Hello there and welcome to Physics with William, where curiosity gets cozy and science takes the scenic route to sleep. Tonight, we're going to wander into one of the biggest and strangest questions in all of science. A question that sounds simple at first, almost like something a thoughtful child might ask while looking up at the night sky. And then, the more you think about it, the more it begins to stretch your mind in every direction. If gravity pulls everything together, why is the universe expanding? It is a fair question. In fact, it is such a fair question that it has bothered some of the greatest scientists who ever lived. Gravity is the force we know best in our bones. It keeps your feet on the floor, pulls raindrops from clouds, gathers rivers toward the sea, holds the moon near Earth, and keeps Earth moving around the sun. Gravity seems to be nature's great collector. It pulls dust into planets, planets into orbits, stars into galaxies, and galaxies into clusters. It is patient, quiet, persistent, and never seems to take a holiday. So if gravity is always pulling, always drawing things inward, always trying to bring matter closer together, then why is space itself getting larger? Why are distant galaxies moving away from us, not just drifting away here and there, but almost everywhere we look, as if the entire cosmic room is gently growing wider, while everything inside it tries to hold on? It's a little like waking up in the morning, making yourself a nice cup of tea, placing a few biscuits on a plate, and then discovering that the table is slowly expanding while the biscuits are politely trying not to slide away from one another. The biscuits may have their own small loyalties. Perhaps one crumb clings to another. Perhaps the whole biscuit stays together because its tiny pieces are bound by forces stronger than the stretch of the table. But the space between the plates, the cups, and the far corners of the table keeps growing. That is not exactly how the universe works, of course, because the universe does not come with a wooden table, a teapot, or the mild disappointment of finding only one biscuit left. But as a gentle beginning, it gives us the feeling of the problem. Things can be bound together locally while the larger stage between them changes. Gravity can pull matter into islands of structure, while the ocean between those islands becomes wider. Before we go any farther, I would love to know where in the world you are listening from tonight. Are you under a clear sky, with stars visible outside your window, or is the universe hiding behind clouds, streetlights, or perhaps a curtain you have not had the energy to open? And if you look around your own room for a moment, what is the nearest thing gravity is quietly holding in place for you? A book on a bedside table, a blanket resting over your feet, a sleepy pet refusing to move, or maybe just you, tucked into the surface of a planet that is spinning through space with far more elegance than most of us manage before breakfast. It is a nice thing to remember, especially at night, that even when the universe feels huge and strange, gravity is still doing its small familiar work all around us. It is holding the lamp where you left it. It is keeping your pillow from floating away. It is making sure that, for now at least, you and Earth remain very much in touch. If you find this kind of slow scientific wandering soothing, or if the thought of galaxies drifting through the dark helps your mind settle after a long day, I would be very grateful if you gave the video a like and perhaps subscribed. It helps this quiet little corner of physics reach others who may also enjoy learning something immense in a calm and unhurried way. And as always, I do hope the subject is interesting enough to keep you gently curious, but not so exciting that it keeps you wide awake. Although if the universe insists on expanding while you're trying to sleep, I suppose we may as well understand what it is up to, so settle in. Let your shoulders loosen. Let the day step back a little. The question waiting for us is not only about gravity and expansion, it is about what space is, what the universe is doing, and how something can pull inward while everything, on the larger scale, still spreads apart. To begin, we need to place ourselves in the right frame of mind. Not the hurried frame of mind we use for clocks, errands, and unread messages, but the slower one, the one that lets us notice that our ordinary expectations were shaped by ordinary things. gravity in daily life is simple enough. Drop a spoon and it falls. Toss a ball upward and it comes back down. Step carefully onto a bathroom scale and gravity immediately offers its opinion, usually without tact. Everything familiar about gravity tells us that it attracts. It does not push. It does not spread things apart. It pulls. This is why the expanding universe seems so surprising. We are used to thinking of the universe as a collection of objects, almost like furniture in a vast room. Stars over here, galaxies over there, clusters farther away, and gravity doing its best to drag them all together. If that were the whole story, you might expect the universe to slow down, gather inward, maybe even collapse one day into an enormous cosmic heap. And for a long time, scientists thought in very similar terms. They imagined that the universe might be like a ball thrown upward. Gravity would pull back on it. The motion might continue for a while, but surely it should slow. Perhaps if gravity had enough strength, the universe might eventually stop expanding and fall back inward. That idea made a certain kind of sense. It matched the gravity we know from falling apples, orbiting planets, and things that go bump in the night after being placed too close to the edge of a shelf. But the universe is not simply matter moving through space in the way a ball moves through air. The expansion of the universe is not quite a spray of galaxies flying outward from a central blast point. It is not like fireworks exploding into an empty sky. That image is tempting, because it is familiar, and familiar images are comforting. We can picture sparks racing away from a centre. We can point to where the explosion happened. We can say, there it began, and there the pieces went. But the universe does not appear to have expanded into empty space from one special location. Instead, space itself has been stretching. The distances between faraway galaxies have grown because the fabric of space between them has grown. Every distant region sees other distant regions moving away, not because everyone is fleeing from one central spot, but because the whole scale of the cosmos is changing. That is a strange sentence to sit with. Space itself can stretch. Not objects stretching like rubber bands in your hands, but the distance between unbound objects increasing because the geometry of the universe changes over time. Nearby things, like your house, your bed, Earth, the moon, the solar system, and even our galaxy, are held together by forces strong enough to resist this cosmic stretching. Your room is not expanding. Your teacup is not slowly drifting away from the saucer because the universe has decided to redecorate. At small scales, gravity and other forces win easily. At large scales, across the immense gaps between galaxy clusters, expansion becomes the dominant fact. The universe behaves differently when you step back far enough, which is a lesson science teaches again and again. The world of the very small is not like the world of the very large. The world of the everyday is not always a good guide to the deep structure of reality. And the universe, rather inconsiderately, does not always arrange itself around human intuition. This is where the question becomes richer. Gravity does pull everything that has mass or energy toward everything else. But it does not automatically mean that all matter must end up in one place. Motion matters. Initial conditions matter. The nature of space matters. The contents of the universe matter. Imagine, very gently, a crowd of people on a vast, slowly widening floor. Some people are close enough to hold hands, and their little groups remain together. Others are so far apart that, even if they begin walking toward one another, the floor between them widens faster than they can close the gap. The groups stay intact, but the distance between groups increases. Again, not perfect, because people and floors are not galaxies in space, and the universe does not need planning permission for its renovations. But it points us toward a useful idea. Gravity shapes structures inside the universe, while expansion describes how the large-scale distances of the universe change. The story becomes even more interesting when we learn how scientists discovered this expansion. It did not come from someone simply staring at the sky and saying, Well, that looks roomier than yesterday. The expansion was revealed through light. Distant galaxies send light across space, and that light carries clues about their motion and the stretching of the universe itself. When astronomers studied that light, they found that many galaxies appeared redder than expected. This reddening suggested that their light had been stretched during its journey. In everyday sound, there is a similar effect when an ambulance passes you. The pitch changes as it approaches and moves away. With light from galaxies, the shift tells us something about cosmic distance and motion. The farther away a galaxy is, in general, the more its light is stretched. This was one of the great clues that space itself is expanding, and there is something wonderfully humbling about that. The universe did not send us a note. It did not write, "Dear humans, I am getting larger, please update your textbooks." Instead, it whispered through the colour of ancient light. It let starlight travel for millions and billions of years, thinning and stretching along the way, until a small species on a rocky planet built telescopes, glass mirrors, careful instruments, and eventually enough coffee-fueled patience to notice the pattern. That is one of the reasons cosmology feels both grand and intimate. It is the study of everything, but it often begins with a tiny measurement, a faint signal, a patient observer, and the question, why does this light look the way it does? Still, the original puzzle remains. If gravity has been pulling all along, should it not have stopped the expansion by now? The answer depends on the balance between the expansion, the amount of matter, and the other ingredients of the cosmos. Gravity does slow the expansion in a certain sense, or at least it tries to. Matter attracts matter. Galaxies tug on one another. Dense regions pull in gas, stars, and dark matter. Over time, gravity builds the cosmic web, a vast pattern of filaments, clusters, and empty regions. Without gravity, the universe would be far less interesting. It might be smooth, thin, and rather dull, like soup with no texture at all. Gravity gives the universe its lumps, its gatherings, its glowing cities of stars. It turns tiny early differences into galaxies. It makes structure possible. It is the reason there are places where stars can form, planets can gather, chemistry can unfold, and someone can eventually lie awake wondering why any of this exists. But the expansion has never needed gravity's permission to continue. Once the universe was expanding, the question became whether gravity could slow it enough to halt it, reverse it, or merely soften it over time. For much of the 20th century, this was one of the central questions in cosmology. Scientists wanted to measure the universe's expansion rate and its density, because those two things seemed to hold the key to its future. Was the universe expanding forever? Would it stop one day? Would it collapse? The answer seemed like it should depend on gravity's strength across the cosmos. In a universe with enough matter, gravity might eventually win. In a universe with too little matter, expansion might continue forever, gradually slowing, but never stopping. It was a majestic tug-of-war, and astronomers were trying to work out who had the stronger grip. Then, as often happens in science, the universe declined to choose one of the neat options on the menu. Observations of distant exploding stars suggested that the expansion of the universe was not slowing as expected. It was speeding up. This was not a small surprise. It was the sort of surprise that makes physicists check their instruments, check their assumptions, check them again, and then quietly consider whether the cosmos is smirking. Something seemed to be driving the expansion faster over time, not in galaxies or solar systems, but across the larger scales of space. We call this mysterious influence dark energy, which is a rather dramatic name for a thing we do not fully understand. It is not dark in the sense of being gloomy or villainous. It is dark because it does not shine, and because its true nature remains hidden. But whatever it is, its effect appears to be real. On the larger scales, the universe is not only expanding, the expansion is accelerating. Now, this does not mean gravity has failed. Gravity is not sitting in the corner feeling embarrassed. Gravity still rules in many places. It holds galaxies together. It gathers clusters. It bends light. It shapes the motion of stars and planets. It forms black holes, those astonishing objects where gravity becomes so intense that even light cannot escape. Gravity is still one of the main authors of cosmic history, but the universe contains more than the matter gravity gathers. The large-scale behavior of the cosmos depends on all its ingredients, seen and unseen, understood and mysterious. Gravity pulls, yes. Expansion stretches, yes. Dark energy somehow appears to make that stretching accelerate. The result is not a contradiction, but a layered story. Different effects dominate at different scales, in different eras, under different conditions. It helps to remember that science often advances by making peace with ideas that first sound impossible. Earth moves, although it feels still. Air has weight, although it feels almost like nothing. Light behaves in ways that refuse to be only waves or only particles. Time itself can slow down depending on speed and gravity. So perhaps we should not be too offended when the universe says, yes, gravity pulls, and yes, I am expanding anyway. The mistake is not in asking the question. The question is excellent. The mistake would be assuming that one familiar fact about gravity must explain the entire behavior of space. Nature is usually more subtle than our first guess, and occasionally more subtle than our second, third, and fourth guesses as well. As we drift into this subject, we will begin close to home, with the kind of gravity we feel every day. We will think about falling objects, orbiting worlds, and why pulling does not always mean collapsing. We will move from Newton's clear and powerful picture of gravity into Einstein's deeper view, where gravity is not just a force acting across space, but something related to the shape and behavior of space itself. Then we will look at what the Big Bang really means, because it was not an explosion in the ordinary sense, and imagining it that way causes all sorts of confusion. We will follow the expansion through cosmic history, watch gravity build galaxies in the middle of it, and finally meet the strange evidence for dark energy, the name we give to whatever is making the universe's expansion speed up. For now, let the question rest in your mind without needing to solve it too quickly. If gravity pulls everything, why is the universe expanding? It sounds like a paradox, but it is more like a doorway. On one side is the gravity of daily life, the familiar tug that keeps us grounded. On the other side is the universe at its largest scale, where space itself changes, distances grow, and the future stretches farther than our instincts can easily follow. Somewhere between those two sides is the answer, not in a single trick or a clever phrase, but in the long, careful story of how we learned to stop picturing the universe as a room full of objects and began to understand it as something far stranger, a place where the room itself has a history. So let us begin with the ordinary feeling of weight, the simple downward pull that has been with you since your first breath, because the road to an expanding universe starts, quite gently, with the fact that everything falls. Everything falls, at least in the world we know best. A dropped key falls toward the floor. A leaf falls from a tree, though it takes its time about it, fluttering down as if negotiating with the air. Rain falls from clouds. Crumbs fall into the awkward little gap between the sofa cushions. And if you have ever tried to carry too many things at once, you already know that gravity has a sharp eye for overconfidence. It is the most familiar of all the cosmic influences because it never feels distant. It is not something you need a telescope to notice. It is there when your feet press into the ground, when your pillow supports your head, when a mug feels heavy in your hand, and when getting out of bed in the morning seems to require slightly more effort than the rest of physics promised. This is why the expanding universe feels so puzzling at first. Gravity seems to be the great downward instruction of reality. It pulls, it gathers, it makes things fall inward. If you hold a stone and let go, the stone does not drift casually toward the ceiling, unless something has gone very wrong with either the room or your breakfast. it drops. If you climb a hill, your body works against gravity. If you roll a ball down a slope, gravity helps it along. Every ordinary example tells us that gravity is a force of coming together, not moving apart. So when we hear that galaxies are rushing away from one another, and that the universe as a whole is expanding, it can sound almost like a contradiction. How can the same universe that pulls apples to the ground also let entire galaxies separate across the dark? The first step is to be careful with what we mean by falling. Falling does not simply mean moving downward. Down is a local idea, and local ideas are very useful until we accidentally try to apply them to the whole universe. On Earth, downward means toward the centre of the planet. If you drop something in your room, it falls toward Earth because Earth is nearby, massive, and very good at being in charge. But someone standing on the other side of the planet has their own downward direction, opposite to yours, and they do not feel upside down. Their feet are pulled toward the same centre from the other side. So even here, in the most ordinary case, down is not a universal direction. It is a relationship between you and the nearest large mass. The universe does not come with a master arrow labelled down. That would be convenient but also rather bossy. Gravity is really about attraction between matter, not a preference for lower shelves. Earth pulls the stone, and the stone pulls Earth as well, though Earth is so much more massive that the stone does nearly all the noticeable moving. The moon pulls Earth pulls the moon, the sun pulls Earth pulls the sun, and everything tugs on everything else. The whole universe is full of these quiet relationships. If you could somehow turn off every other force and remove every complication, bits of matter would tend to move toward one another under gravity. That part is true, but the real universe is not a still room where objects begin at rest and politely wait for gravity to decide what happens. Things are already moving. They have histories, they have directions, they have speeds. And gravity, though persistent, does not erase all motion instantly. It bends motion. It redirects it. Sometimes it captures. Sometimes it only slows. Sometimes it turns what might have been a straight line into a long curve that never quite becomes a crash. This is easiest to see with orbits. The moon is falling toward Earth, but it is also moving sideways fast enough that it keeps missing. That may sound like a joke, and in a way it is one of nature's best jokes. An orbit is a kind of continuous falling where the falling object never reaches the ground because the ground curves away beneath it. The moon is not floating because gravity forgot about it. It is held by gravity. It is always being pulled inward, but its sideways motion carries it around Earth. A satellite above us does the same. It is falling around the planet, not because there is no gravity up there, but because gravity is guiding its path. Astronauts in orbit are not weightless because gravity has vanished. They feel weightless because they and their spacecraft are falling together. It's a very elegant arrangement, though perhaps not one you would want to explain while trying to drink tea from a floating pouch. This already softens the idea that gravity simply makes things collide. Gravity can hold things in motion. It can create stable patterns. It can make planets circle stars for billions of years without falling into them. A planet does not crash into the sun because it has sideways motion. If it moved too slowly, it could spiral inward. If it moved too quickly, it might escape. But at the right speed, gravity and motion combine into an orbit. So gravity pulling does not always mean immediate collapse. It often means curved paths, long dances, and arrangements that last far longer than any human schedule, even the ones that feel endless, because someone used the phrase quick meeting. Now think about throwing a ball. If you toss it gently, it rises and falls back. Throw it harder, and it travels farther before landing. Throw it far harder still, and in principle, it could curve around Earth. Make it fast enough, and it could escape Earth's gravity altogether. Gravity still pulls on it, but not enough to bring it back. This idea matters because gravity is not magic glue. It does not guarantee reunion. It competes with motion. If something has enough outward motion, it can keep going away even while gravity tries to slow it. The pull is still real. The slowing is still real. but the object may never return. In everyday life, we do not usually throw things at such speeds, which is probably just as well for windows, neighbours, and the general peace of the street. The expanding universe is not exactly like throwing a ball, but the comparison helps us separate two ideas that are often mixed together. Gravity can pull, and yet motion can continue. A galaxy can be attracted to other galaxies, and yet the distance between very distant galaxies can still grow. The key difference is that cosmic expansion is not simply galaxies flying through space like shrapnel. It is the stretching of space itself between galaxies that are not bound together. Still, even before we get to the deeper idea of stretching space, it is useful to remember that pulling does not automatically defeat moving apart. A tug-of-war can be real, even if one side is still sliding. There's also the matter of scale. Scale is one of the quiet troublemakers in science. A rule that dominates in one setting may be nearly irrelevant in another. On the scale of your room, the expansion of the universe has no practical effect. The atoms in your bedside table are held together by forces much stronger than cosmic expansion. Earth is held together by gravity and internal forces. The solar system is held together by the sun's gravity. The Milky Way is held together by its own gravity, along with the unseen mass we call dark matter. These systems are bound. They have gathered into stable structures, or at least stable enough for our purposes. The distance between your eyes is not growing because the universe is expanding. Your shoes are not slowly migrating to opposite corners of the room, unless you kicked them there yourself and are now blaming cosmology. But between galaxy clusters, across enormous distances where matter is thinly spread, the situation changes. There may be no strong local bond holding one cluster to another. The space between them can grow, and as it grows, the distance increases. Gravity still reaches across that distance, but its influence becomes weaker with separation, and the expansion of space can dominate the overall behaviour. It is not that gravity stops existing. It is that, on the larger scales, gravity does not always have enough local grip to keep every distant region connected in the same way. This is where an everyday analogy can be helpful, provided we do not take it too literally. Imagine raisins in a loaf of bread as the dough rises. The raisins are not crawling away from each other through the dough. The dough between them expands, and the distances between raisins increase. Raisins close together may remain fairly close. Raisins far apart become farther apart as more dough appears between them. The universe is not actually a loaf, thankfully, because that would raise difficult questions about who left it in the cosmic oven. But the image helps with one important idea. Expansion can mean the growth of the space between things, not simply objects travelling outward from a central point. A balloon with dots on its surface is another common example. As the balloon inflates, each dot sees other dots moving away across the surface. There is no special centre on the surface itself. Every dot can feel as though it is at the centre of the expansion, because every distant dot moves away. Again, the universe is not the skin of a balloon, and it does not need to be expanding into some larger room in the way a balloon expands into air. But it gives a feeling for how every place can see expansion without there being one privileged middle point. If all of space is changing at scale, then every observer in every galaxy can look out and see distant galaxies receding. The difficult part is that our brains are trained by objects inside space, not by space itself. We know how smoke expands into a room. We know how water spreads across a floor, usually after someone has said, "Do not worry, I've balanced this perfectly." We know how crowds spread out in a park. In all these cases, something expands into an already existing area. But when cosmologists talk about the universe expanding, they do not mean it is expanding into a surrounding emptiness in the usual sense. They mean distances within the universe are increasing over time. The stage itself is changing. That is not a normal household experience unless your house is much stranger than mine. This is why the question can feel slippery. We ask why gravity does not pull everything back together because we picture galaxies as objects thrown into a fixed space. We imagine they should slow, stop, and fall inward. That picture is not completely useless, but it is incomplete. The universe is governed by the behavior of space as well as the matter in it. Gravity is involved, deeply involved, but gravity in modern physics is not merely a force tugging objects through a fixed background. It is connected to the shape and evolution of space itself. That idea will become clearer when we reach Einstein's view, but we can begin preparing for it now by loosening our everyday picture. Consider a group of ants walking on a rubber sheet that is being stretched. If two ants are close together and holding a tiny crumb between them, they may remain together. If two ants are far apart and trying to reach each other, the sheet stretching between them may make the journey harder. From the ant's point of view, other ants may seem to drift away even if the ants themselves are not sprinting. The local relationships and the larger stretching are different effects. Now, ants on rubber sheets are not famous for their cosmological insights, mostly because grant funding remains limited, but the image helps. There can be local structure and global expansion at the same time. In the real universe, this is exactly what we see. Galaxies are not spread perfectly evenly like dots on a school diagram. They gather into groups and clusters. They form long filaments and enormous walls, surrounding vast regions that are comparatively empty. This pattern is often called the cosmic web, and gravity is the weaver. In the early universe, matter was more smoothly distributed, but not perfectly smooth. There were tiny differences in density. Some regions had slightly more matter than others. Gravity amplified those differences. The denser regions pulled in more material, becoming denser still. Over time, stars formed, galaxies assembled, clusters grew, and the universe became lumpy in a beautiful and complicated way. Gravity was not sitting helplessly, while expansion carried everything apart. It was busy building the structures that make the universe worth looking at. But gravity's work is local compared with the whole. It can gather matter where matter is close enough and dense enough. It can form galaxies within an expanding background. This may feel contradictory, but it is not. A city can grow while the country around it changes. A knot can tighten in a rope while the rope is being stretched. A puddle can freeze in one corner of a garden while the air temperature elsewhere shifts. Different processes can happen at the same time in different places or at different scales. The universe does not have to choose only one behavior. It can clump and expand. It can gather here and separate there. It can build islands while widening the seas between them. This also helps explain why we do not see expansion inside galaxies. The Milky Way is gravitationally bound. The stars in it orbit within the galaxy's gravitational field. Our neighbouring galaxy, Andromeda, is actually moving toward the Milky Way, not away from it, because the local gravitational attraction between our galaxies is stronger than the expansion effect at this distance. In a few billion years, the two galaxies are expected to merge into a larger system. So even in an expanding universe, some things approach each other. This is not an exception that breaks the idea of expansion. It is a reminder that expansion is a large-scale pattern, not a rule that every single distance between every pair of objects must increase. A useful way to say it is this: the universe expands on average, across the larger scales, but local gravity can override that expansion in regions where matter is bound together. The word average is doing important work there, though it is not a very glamorous word. It does not sparkle, it does not make the documentary trailer more dramatic, but it is honest. Cosmology often deals with large-scale averages. When you zoom out far enough, beyond individual galaxies and clusters, the universe looks broadly smooth. At that scale, expansion describes the overall behaviour. Zoom in, and gravity has made all sorts of interesting messes. Stars, galaxies, clusters, and people who leave cables tangled in drawers. The universe is smooth from far away and complicated up close, which is also true of many things, including carpets, soups, and family holidays. There is another everyday misconception worth clearing away gently. When we say galaxies are moving away because space expands, it does not mean space is a substance pushing them along like a river current. Space is not a wind blowing through the universe. It is not a syrup. It does not have little hands. Expansion means that the distance described by the geometry of the universe changes over time. That may sound less cozy than raisins in bread, but it is closer to the physics. The language is difficult because we are trying to describe something outside ordinary experience using ordinary words. Words like stretch and fabric and expansion are useful, but they can mislead if we forget they are guides, not exact copies of reality. So what does it mean for a galaxy to be carried away by expanding space? It means that when astronomers measure the distances to faraway galaxies and how their light has been stretched, they find a consistent pattern. The farther away a galaxy is, the faster it appears to recede from us due to the expansion of space. This is not because we are special, or because Earth is at the centre. Observers in those distant galaxies would see the same kind of pattern. From their point of view, we would be the ones receding. Every distant observer sees the large-scale universe expanding around them. That is one of the great shifts in perspective that cosmology asks of us. We are not at the centre of the expansion. There is no central seat, no reserved cushion, no little sign saying humans sit here. The expansion belongs to the whole stage. If that feels strange, think again about the balloon surface. Every dot sees every other dot moving away as the surface grows, and no dot on the surface is the centre of the surface's expansion. The actual centre of the balloon lies in the higher dimensional space outside the surface. But for creatures living only on the surface, that centre is not part of their world. Our universe may not work exactly like that, but the lesson is useful. Expansion does not require a central location inside the universe. It can be a property of the whole geometry. Gravity, meanwhile, is always trying to reduce separations where it can. If two galaxies are close enough and moving slowly enough relative to one another, they may become bound. If they are far apart and the space between them is expanding rapidly, they may never meet. This is not because gravity chooses favourites. It is because the outcome depends on distance, motion, mass, and the state of the universe itself. Gravity is universal, but universal does not mean all-powerful in every situation. A whisper is still sound, even if it cannot be heard across a storm. Gravity reaches far, but the universe is vast and vastness matters. There is a gentle lesson hidden here about intuition. Our first idea of gravity comes from falling. Falling is immediate and convincing. It happens right in front of us. Expansion is not immediate. You cannot watch two distant galaxies separate with your eyes over a cup of tea. The evidence comes from telescopes, long observations, careful measurements of light, and a chain of reasoning that took many minds to build. So the familiar idea feels stronger than the distant one. We trust the falling spoon more than the receding galaxy, because one dents the floor and the other arrives as a faint smudge on a detector. But science has often required us to trust careful measurement beyond the reach of direct feeling. Earth feels still, but it rotates. The sun seems to cross the sky, but Earth is turning. Solid matter feels full, but atoms are mostly empty space by volume. Common sense is a useful tool for kitchens and stairs, but the universe is bigger than a kitchen, and considerably less worried about stairs. The everyday mystery, then, is not that gravity and expansion contradict each other. It is that they belong to different levels of description. Gravity makes things fall, orbit, gather, and bind. Expansion describes the changing scale of the universe across enormous distances. In small bound systems, gravity and other forces keep structures intact. In the great spaces between unbound systems, expansion increases distances. The universe can do both, just as the ocean can have waves on its surface while the tide slowly rises, or a loaf can hold raisins while the dough between them grows, or a sleepy listener can be both curious and drifting at the same time. This is also why the phrase flying apart can be misleading, though it captures the feeling of the question. Galaxies are not flying away from a central explosion through empty space like fragments of a shattered vase. Many galaxies have their own local motions, of course, and they can move through space because of gravitational interactions. But the grand recession of distant galaxies is mainly about the expansion of space between them. The difference matters. If the universe was simply an explosion, there would be a center, an edge, and a surrounding emptiness. But the observable universe shows expansion in all directions, with no evidence that we occupy a central blast point. The Big Bang was not an explosion at one location in space. It was a hot, dense, early state of space itself, followed by expansion everywhere. That idea is harder to picture, but it removes many false puzzles. A small room offers no good model for this, because rooms have walls and centers. A firework offers no good model, because fireworks explode into pre-existing air. Even bread dough and balloons only take us part of the way. The real subject is the universe's own geometry and history. Still, our everyday examples are not useless. They help us untangle the emotional knot. We know gravity pulls. We know things can keep moving while being pulled. We know bound systems can resist larger changes. We know expansion can happen between objects rather than inside them. Each small understanding takes away a little of the apparent contradiction, and perhaps that is the best way to approach a question this large. Not by forcing the whole answer into one clever image, but by letting ordinary experiences prepare the mind for less ordinary ones. The falling key tells us gravity attracts. The orbiting moon tells us attraction can create endless falling without collision. The thrown ball tells us motion can continue against a pull. The rising dough tells us distances can grow because the space between markers increases. The Milky Way tells us bound structures can remain intact. Distant galaxies tell us the universe on the larger scales is changing. Put these together, and the mystery becomes less like a wall and more like a path. At the end of that path stands a deeper question. What is gravity really? For everyday life, it is enough to call it a pull. That simple description works beautifully for falling objects, planets, tides, and the small inconveniences of dropped toast. But when we ask about the whole universe, we need a more powerful picture. We need to know how scientists first turned gravity from a familiar feeling into a mathematical description of nature, and how that description made the heavens seem orderly, predictable, and almost mechanical. Long before the expanding universe was discovered, before galaxies were known to be galaxies, before anyone imagined dark energy, there was the great problem of motion in the sky and motion on Earth, and one of the first people to show that they were part of the same story was Isaac Newton. Long before anyone knew that the universe was expanding, long before astronomers had measured galaxies slipping away into the dark, and long before the phrase dark energy had wandered into physics like a mysterious guest who refuses to explain why they are here, gravity already had a story. It was a story written in falling stones, circling moons, ocean tides, and the steady motions of planets against the night sky. People had watched the heavens for thousands of years, carefully tracking the sun, the moon, the wandering planets, and the stars that seemed fixed in place like little pins in a deep black cloth. They noticed patterns, they built calendars, they predicted eclipses. They gave names to constellations, sometimes with impressive imagination, sometimes with the slightly suspicious confidence of people who looked at 6 stars and saw a hunter, a swan, or a goatfish. But for a very long time, the sky and Earth felt like 2 different realms. Things on Earth fell, broke, rolled, splashed, and caused mild inconvenience. Things in the heavens moved with a clean and distant regularity, as though they belonged to a more perfect kind of nature. Then came Isaac Newton, a man whose name has become so closely tied to gravity that even mentioning an apple near a science teacher can summon him like a ghost with excellent hair. The famous apple story is probably not quite the cartoon version many of us learned, with Newton sitting under a tree taking a direct fruit-based blow to the head and instantly inventing gravity between snacks. the more likely version is quieter and, in a way, more interesting. Newton saw an apple fall, or thought about apples falling, and asked why the same pull that brings fruit to the ground might not also reach upward, outward, all the way to the moon. That question was the key. Not simply why does an apple fall, but could the fall of an apple and the orbit of the moon be part of the same physical story? It is hard to overstate how powerful that idea was. In everyday life, the apple falls straight down and stops when it hits the ground, hopefully not on anyone who is trying to have a peaceful afternoon. The moon, by contrast, does not fall to Earth. It moves around us, month after month, with a reliability that made it useful for calendars, tides, and late-night romantic scenes in films. To connect those two things required a leap of imagination. Newton realised that the moon could indeed be falling toward Earth, but because it was also moving sideways, it kept missing. Earth curves away beneath it as the moon continues around. The apple has no such luck. It begins close to the ground and with no great sideways speed, so its fall is short, direct, and usually ends in bruised fruit. The moon has enough sideways motion to turn falling into orbit. This was one of the great unifications in science. It suggested that the heavens were not governed by one set of rules and Earth by another. The same gravity that pulls a stone from your hand also helps guide planets around the sun. Suddenly, the universe became more coherent. The messy ground and the majestic sky were connected by a single principle. It was as if someone had discovered that the quiet ticking of a clock in the hallway and the movement of the stars overhead were keeping time to the same hidden mechanism. For a mind trying to understand nature, that is a deeply satisfying thought. Also a slightly dangerous one, because once humans discover a hidden mechanism, we become very tempted to believe we can understand the whole machine. Newton did not discover gravity in the sense that no one had ever noticed falling before. People had been noticing falling for as long as people had been dropping things, which is to say, from the very beginning of people. What Newton did was describe gravity as a universal attraction between masses. Every piece of matter attracts every other piece of matter. Earth pulls the apple pulls Earth, the sun pulls the planets pull the sun, and even you, resting quietly wherever you are, exert a tiny gravitational pull on everything around you. Your chair, your lamp, the walls, the moon, distant stars, all of it is involved in one enormous network of attraction. Your personal pull on a galaxy far away is so small that even calling it tiny feels generous, like complimenting a dust mote on its athletic ability, but in principle it is there. Newton also showed that gravity weakens with distance. The farther apart two objects are, the weaker their attraction becomes. This matters because it explains why nearby masses dominate our experience. Earth pulls you strongly because it is close and massive. The sun also pulls on you, and so does the moon, but you do not feel those pulls in the same direct way as your weight on the ground. A mountain pulls on you too, but not enough to ruin your walk unless the path is steep, in which case gravity in your knees may hold a lengthy discussion. The universe is full of gravitational pulls in every direction, but most are faint compared with the local giants. Newton's genius was not only in saying these things, but in turning them into precise rules. With his laws of motion and gravity, he gave scientists a way to calculate how objects move. A falling object, a swinging pendulum, a cannonball, a planet, a comet, a moon, all could be described within the same framework. The world began to look like a clockwork system, vast, orderly, and predictable. If you knew where something was, how fast it was moving, and what forces acted on it, you could, at least in principle, predict where it would go next. This was a remarkable shift. Nature was no longer just observed, admired, feared, and occasionally blamed for bad weather. It could be modelled, it could be anticipated, it could be placed under the gentle but firm discipline of mathematics. The clockwork image became one of the defining ideas of classical physics. The universe was imagined almost like an immense mechanical device, made of parts moving according to reliable laws. Planets swept around the sun in regular paths. Moons circled planets. Comets returned after long absences, like dramatic relatives who appear once in a lifetime and make everyone nervous. Tides rose and fell because the moon and sun pulled on Earth's oceans. Projectiles followed arcs. Clocks ticked. Machines could be built. Bridges could be designed. Navigation improved. The same physics that described the heavens helped with engineering, artillery, architecture, and eventually the industrial world. Newton's gravity did not merely explain why apples fall. It helped build the modern age. It also encouraged a certain confidence. If the universe was a clock, then perhaps it could be understood completely by knowing the positions and motions of all its parts. This idea later became associated with a famous thought experiment, in which an intelligence with complete knowledge of every particle could predict the entire future and reconstruct the entire past. It is a grand and slightly unsettling vision. Everything determined, everything calculable, every falling leaf, every orbiting planet, every spilled cup of tea, all part of the same mechanical unfolding. It is not exactly a comforting bedtime thought, unless you find determinism soothing, in which case you're welcome to enjoy that in your own very predictable way. For the question of the universe as a whole, Newton's picture had an important consequence. If gravity is a universal attraction, then every star should attract every other star. Every bit of matter should pull on every other bit. This raised a problem that was not immediately easy to solve. What happens if the universe is filled with matter everywhere? Would all of it pull together? Would the stars collapse toward one another? Could the universe be stable? Newton himself lived before astronomers understood galaxies as vast systems of stars beyond our own. In his time, the universe was not pictured the way we picture it now. Still, the problem was present in seed form. A universe governed by universal gravity seems to have a tendency toward clumping. Matter attracts matter. If there are small irregularities, gravity can amplify them. A slightly denser region pulls in more matter, becoming denser still. This is very useful for making stars and galaxies, but it makes a perfectly static universe difficult to imagine. If everything pulls on everything else, why does it not all fall together? One answer that people sometimes imagined was that the universe might be infinite and filled evenly with stars in all directions. If matter extends forever, perhaps every pull is balanced by another pull from the opposite direction. A star is pulled left, but also right, up, but also down, in every direction, equal attraction. That sounds neat, a cosmic balance so tidy it practically folds its own laundry. But it hides difficulties. Perfect balance is fragile. If anything is even slightly uneven, gravity can begin to gather matter into clumps, and an infinite static universe filled with stars creates other puzzles too, including the old question of why the night sky is dark if stars fill space endlessly in every direction. That puzzle would eventually become its own doorway into cosmology. The important thing is that Newton's gravity made the universe dynamic in spirit, even when people wanted to imagine it as static. Gravity is not a passive decoration. It acts, it changes motion, it pulls structures together, it makes stillness suspicious. If you place masses in space and let gravity work, they tend to move. They fall, orbit, scatter, merge or collapse depending on their starting conditions. A perfectly frozen cosmos is not the natural outcome of Newtonian gravity, unless you arrange it very carefully, and the universe has never seemed especially interested in careful arranging for human convenience. Even so, Newtonian gravity worked beautifully for most purposes. It described the solar system with astonishing success. Astronomers could predict planetary motions and eclipses. When Uranus was observed to move in a way that did not quite match expectations, scientists used Newton's laws to infer the presence of another planet tugging on it. That led to the discovery of Neptune. Imagine the confidence that gives a scientific theory. Not only can it explain what you see, it can point into the dark and say, Something must be there. And then, when telescopes look, there it is. That is not a small achievement. That is physics politely showing off. Newton's framework also shaped how people thought about space and time. Space was the stage where matter moved. Time was the steady clock running in the background. Forces acted between objects, and motion unfolded against this fixed arena. It was a clear picture, strong enough to guide science for centuries. In this view, if the entire universe were expanding, one might naturally imagine galaxies moving through absolute space, like particles flying apart after some original outward motion. Gravity would pull backward on that motion. The big question would be whether the outward motion was strong enough to continue, or whether gravity would eventually slow it to a halt and reverse it. That way of thinking is not foolish. In fact, it captures part of the intuition cosmologists used for a long time. If you throw a ball upward, gravity slows it. If it is thrown too slowly, it falls back. If it is thrown fast enough, it escapes. Applied loosely to the universe, one might wonder whether cosmic expansion is like that. Was matter launched outward with enough speed to keep expanding forever, or would gravity eventually pull it all back? This simple picture is not the final one, but it is a useful stepping stone. It shows why the amount of matter in the universe matters. More matter means more gravity. More gravity means more slowing. Less matter means expansion has an easier time continuing. But Newton's framework has limits when the subject becomes the universe itself. Newtonian gravity assumes space and time are fixed backgrounds. They are the arena, not the actors. Matter moves through space, and time measures the motion. That works extremely well for planets, projectiles, and most engineering. But when we ask about the entire cosmos, the arena can no longer be treated so casually. If all matter in the universe is involved, if space extends in every direction, if gravity is universal, then perhaps space and time themselves are not merely a stage. Perhaps they are part of the drama. This is where Newton's picture, magnificent though it is, begins to feel like a beautifully made map that does not quite cover the territory beyond its borders. There were other clues that Newton's gravity might not be the final word. One of the most famous involved Mercury, the innermost planet. Its orbit did not behave exactly as Newtonian calculations predicted, even after accounting for the pulls of the other planets. The difference was small, but persistent. Small differences are often where new physics hides, like a cat under a blanket pretending not to be involved. For many purposes, Newton's theory remained astonishingly accurate, but at extremes, near strong gravity, or when great precision was required, something deeper was needed. Another issue was the way gravity seemed to act across empty space. In Newton's theory, masses attract one another at a distance. Earth pulls the moon without any visible rope, rod, or messenger running back and forth between them. Newton himself was cautious about explaining the mechanism behind this attraction. He gave a rule for how gravity behaves, but he did not claim to know exactly how one object reaches across space to influence another. This action at a distance troubled many thinkers. It worked mathematically, but the underlying picture felt incomplete. How does the sun tell Earth how to move? How does Earth tell the moon? Does gravity act instantly? If the sun vanished, would Earth know at once? Or would the news travel somehow? Questions like these would later matter enormously. For a long time, though, Newton's theory was so successful that these worries could be set aside in many practical contexts. A theory that predicts planets, tides, falling bodies, and comets earns a great deal of patience. It is a bit like a slightly mysterious old clock in the hallway. You may not understand every gear inside it, but if it tells the time correctly for 200 years, you become inclined to trust it. Newtonian gravity became the language of celestial mechanics, the science of heavenly motion. It gave the universe a sense of order that was both powerful and calming. The planets were no longer wandering lights with mysterious personalities. They were bodies moving under law. The moon was not simply a silver companion of myth and tide, but an object in continual free fall around Earth. The heavens had become mechanical. This clockwork cosmos also shaped the emotional atmosphere of science. It suggested that nature was rational. Complicated, yes, but not chaotic beyond understanding. The same rule could apply in a garden and in the sky. A person standing under a tree and a planet moving through the darkness belong to one universe, not two. There is something quietly beautiful in that unity. It means our local experiences, if understood deeply enough, can lead outward. A falling apple can become a path to the moon. A tide on the shore can become a clue to celestial attraction. The weight of your own body can become a reminder that you are part of the same gravitational network as planets and stars. Not separate from the cosmos, not merely looking up at it, but physically included in it. And yet, when we return to the question that began our journey, the clockwork picture leaves us uneasy. If gravity is always attractive, and if the universe contains matter everywhere, a static cosmos seems unnatural. The clock wants to move, the gears want to turn, matter wants to gather. The universe, under Newton's gravity, is difficult to keep still. That is the beginning of the tension. For centuries, many people assumed the universe as a whole was eternal and unchanging on the larger scales. Stars might move, planets might orbit, objects might form and fade. But the grand cosmic arrangement was often imagined as fixed. Newton's gravity did not easily support that comfort. It whispered that matter should respond, that structures should evolve, that the heavens might not be as unchanging as they appear from a human lifetime. Of course, Newton did not discover the expansion of the universe. That would come much later, through telescopes, spectroscopy, and the realization that many fuzzy patches in the sky were not small clouds inside our galaxy, but entire galaxies far beyond it. Newton gave the tools and the mindset that made later questions possible. He taught science to ask how motion changes under gravity. He gave the universe a mechanical grammar. But when the scale grew to include all of space, the grammar needed new sentences. This is why Newton's gravity is both essential and incomplete for our story. It explains why gravity should resist expansion. It explains why matter gathers into structures. It gives us the intuition that an expanding universe might slow under its own attraction. It helps us understand why the question feels so natural in the first place. If you learned gravity from Newton, and in daily life we mostly do, then an expanding universe seems like something that ought to require an explanation. Things pull together. Why are the biggest distances growing? The answer, from a Newtonian point of view, begins with motion and balance. Expansion could continue if the initial outward motion were large enough, and if the matter density were not high enough to reverse it. Gravity would still pull, it would still slow. It would still shape matter into galaxies and clusters, but it might not stop the overall expansion. This is already a reasonable beginning. Yet it does not reach the heart of the modern picture, because in the modern picture, gravity is not simply a force pulling objects through space. Space and time are not just the stage. They can bend, they can stretch, they can evolve. The universe is not merely a clockwork machine placed inside a fixed room. The room itself can change. That idea would have sounded strange in Newton's world. It still sounds strange now, if we are honest. We are comfortable with objects moving. We are less comfortable with space itself having behaviour. But the cracks in the old picture slowly widened. Light, electromagnetism, precise planetary motion, and the deep question of how gravity communicates across space all pointed towards something new. And eventually a patent clerk with untidy hair and a habit of chasing simple questions to their most unsettling conclusions would take Newton's dependable cosmic clock, listen carefully to its ticking, and realise that the clock was not standing on an unmoving shelf after all. The patent clerk was Albert Einstein, and he did not begin by trying to make the universe feel strange. That is one of the charming things about him. He began with questions that were almost childlike in their simplicity, the sort of questions that sound harmless until they quietly remove the flaw from under an entire worldview. What would it be like to ride alongside a beam of light? What does it mean for two events to happen at the same time? How does a person in motion describe the world compared with a person standing still? These are not questions that require a grand laboratory at first glance. They can begin in the mind during a walk at a desk, or perhaps while pretending to do paperwork that suddenly seems less important than the structure of reality. And from those questions came a new picture of time, space, gravity, and eventually the universe itself. In Newton's world, space and time were like the stage and the clock. Space was where things happened. Time was when things happened. The stage did not bend, stretch, wrinkle, or join the performance. It simply sat there, perfectly still and available, while planets, apples, comets, and occasionally startled humans moved around on it. Time ticked in the background at the same rate for everyone, everywhere, with the calm confidence of a very strict school teacher. This view worked beautifully for everyday motion, and even for the motions of planets. It was clear, useful, and deeply sensible. But nature, as we have already seen, is not required to remain sensible just because we have grown fond of a good explanation. Einstein began by noticing that light behaved in a way that did not fit comfortably inside the old picture. The speed of light appeared to be the same for all observers, no matter how they were moving. That sounds innocent until you think about ordinary speeds. If you are walking down a train carriage while the train moves forward, someone standing beside the tracks would describe your speed as your walking speed added to the train's speed. If you throw a ball from a moving car, the ball's motion depends on both the throw and the car. Speeds usually add and subtract in a friendly everyday way. Light refused to behave so politely. Whether you moved toward a beam of light or away from it, light still passed you at the same speed. It was as if the universe had written this rule in very firm ink and left all human intuition to shuffle awkwardly around it. To preserve that rule, something else had to give. Einstein realized that space and time could not be fixed and absolute in the way Newton imagined. Different observers, moving differently, would not always agree on distances or on the timing of events. Time could slow, lengths could change. Simultaneity, the idea that two things happen at the same time, was not universal. This was special relativity, and even before gravity entered the story, it had already made reality more flexible than most people had hoped before lunch. Time was no longer a single clock shared by the cosmos. Space was no longer a universal measuring grid. They were linked together into something deeper, a combined structure that we now call spacetime. Spacetime is one of those words that can sound grand and mysterious, but the basic idea is straightforward enough if approached gently. In ordinary life, we describe an event by saying where it happened and when it happened. The kettle boiled in the kitchen at 7 in the morning. The cat knocked over the glass on the table at the precise moment nobody was watching. A star exploded in a distant galaxy millions of years ago. Location and time belong together because events need both. Einstein's work showed that they are not separate containers. They are connected parts of one structure, and different observers may slice that structure differently depending on how they move. The universe was not a stage plus a clock. It was a woven arrangement of space and time together. That was already a revolution, but Einstein was not finished. Special relativity dealt with motion at steady speeds, without acceleration and without gravity. Gravity still needed to be brought into this new picture. Newton had described gravity as an attractive force between masses. It worked wonderfully, but it left a deep question behind. How did gravity reach across empty space? How did Earth know the sun was there? How did the moon know how to move around Earth? Newton had given a rule for the pull, but not a deeper explanation for the mechanism. Einstein wanted something more complete. The key came through another simple thought. one so simple that it seems almost unfair how much physics was hiding inside it. Imagine being inside a sealed room with no windows. If the room is sitting on Earth, you feel your feet pressed to the floor because gravity pulls you downward. Now imagine the same room far out in empty space, being accelerated upward by a rocket. You would also feel pressed to the floor. Inside the room, without looking outside, it would be very difficult to tell whether you were feeling gravity or acceleration. This connection between gravity and acceleration became one of Einstein's guiding clues. It suggested that gravity might not be an ordinary force in the old sense. It might be related to the way motion itself is described in curved spacetime. The result was general relativity, published after years of intense work. In this theory, gravity is not simply a pull acting across a fixed background. Matter and energy affect the shape of spacetime, and the shape of spacetime guides how matter and light move. A planet orbits the sun not because the sun reaches out with invisible strings, but because the sun curves the spacetime around it, and the planet follows the natural path through that curved geometry. The planet is still, in a sense, moving freely, but freely through a landscape that has been shaped by mass. It is a bit like walking across uneven ground. You may feel as if you are simply following your own steps, but the slope and shape of the ground quietly influence where those steps go. Of course, spacetime is not literally ground, and the sun has not placed a dent in a cosmic mattress in any ordinary way. But the idea helps us loosen the old image of gravity as a mysterious pull and replace it with the deeper image of geometry. The popular rubber sheet picture tries to show this. Place a heavy ball on a stretched sheet, and smaller balls roll around the dip. It is useful, but it has limits. For one thing, the rubber sheet needs ordinary gravity to pull the balls down into the dip, which means it uses gravity to explain gravity, a little like explaining tea by pointing to a teapot and hoping no one asks too many follow-up questions. Also, real space-time curves in more dimensions than the rubber sheet can show. Still, the image gives the right emotional direction. Mass changes the geometry around it. Motion follows that geometry. Gravity becomes the shape of the world, not merely a force inside it. This new view also changed what it meant to talk about the universe as a whole. In Newton's picture, the universe could be imagined as matter spread through fixed space. If matter moved, it moved through that fixed stage. But in Einstein's theory, space itself is part of the physical system. It can curve, it can change, it can respond to the matter and energy within it. This was the opening through which modern cosmology entered. Once space-time became dynamic, the universe itself could have a history in a deeper sense. Not just stars moving around inside space, but space changing with time. At first, even Einstein did not fully welcome this consequence. Like many scientists of his era, he assumed that the universe on the larger scale was static. The stars might move, and systems might change. But the overall cosmos was thought to be eternal and unchanging. This was not a foolish belief. Before the evidence for cosmic expansion, a static universe felt natural. The night sky looked broadly steady from one generation to the next. Human lives are short, and the heavens are patient. If you watch the stars for one evening, they wheel overhead. If you watch them across the seasons, familiar patterns return. Nothing about the ordinary sky tells you that the entire universe is stretching. It does not make a creaking sound. It does not politely announce that the distance to distant galaxies has increased since dinner. But Einstein's equations resisted a static universe. When applied to the cosmos as a whole, they seem to suggest that the universe should either expand or contract. A perfectly still universe was unstable, like balancing a pencil on its point and hoping the cat does not enter the room. Gravity from all the matter in the universe should affect the geometry of space-time. The cosmos could not simply sit there forever unchanged without some additional ingredient. To make his model static, Einstein introduced what came to be called the cosmological constant, a term that could act somewhat like a repulsive effect on the larger scales, balancing gravity and holding the universe still. This detail is important because it shows something human about science. Einstein had produced a theory that allowed the universe to be dynamic, but he preferred a static cosmos because that was the expectation of the time, so he adjusted the theory to match that expectation. This was not dishonesty. It was a reasonable move based on what seemed known. Scientists are not floating brains made of pure logic. They live in historical moments, they have assumptions, they drink coffee, misplace notes, and sometimes add terms to equations because the universe appears to require a bit of tidying. Later, when evidence for expansion became strong, Einstein reportedly regretted introducing the constant for that reason, though the exact famous wording often attached to this regret is debated. In a rather amusing twist, a modern version of the cosmological constant returned to physics much later in connection with dark energy. The universe has a taste for dramatic callbacks. While Einstein was working with his theory, others explored its implications for the whole cosmos. Alexander Friedmann found solutions in which the universe could expand or contract. Georges Lemaitre, a Belgian priest and physicist, also developed the idea of an expanding universe and connected it to observations of galaxies. This is one of the quiet pleasures of the history of science. A theory opens a door, and different minds walk through it from different directions. Einstein had changed the rules of gravity, but the expanding universe emerged through the combined work of theorists and observers, each following clues that were not yet part of common understanding. The crucial point for our question is that Einstein's universe is not a rigid container. It is not a box filled with galaxies. It is more like a changing geometry whose scale can grow or shrink. If the universe expands, it is not that galaxies are merely flying through a pre-existing void from a central explosion. Rather, the distances between widely separated regions of space increase, because the space-time geometry itself evolves. Gravity still matters, but it now belongs to the behavior of space-time. The same theory that explains why light bends near the sun also allows the large-scale universe to stretch. This makes the original puzzle less surprising, though not less wonderful. In Newton's picture, one might ask how objects can keep moving apart if gravity pulls them together. In Einstein's picture, the question becomes richer. How does the geometry of the universe evolve under the influence of all its contents? Matter, radiation, dark matter, and whatever dark energy is, all contribute to the cosmic story. Gravity is not just a hand pulling objects inward, it is the relationship between the universe's contents and the shape and motion of space-time. Expansion is not something happening despite space-time, it is a behavior of space-time. To make this feel less remote, think about the surface of Earth. Two travellers starting at the equator and walking north along lines of longitude may begin far apart. As they continue, their paths draw closer, not because a force pulls them sideways, but because the surface they walk on is curved. The geometry of the surface shapes the meaning of straight paths. Now, do not stretch this analogy too far, because the universe is not simply Earth's surface, and time is involved in a deeper way. But it shows how geometry can guide motion without looking like an ordinary push or pull. General relativity takes that idea and applies it to space-time itself. Objects follow natural paths through curved space-time, and those paths can look to us like gravitational motion. Light follows this curved geometry too. This was one of the early tests of general relativity. During a solar eclipse, astronomers measured the apparent positions of stars near the Sun and found that their light had been bent by the Sun's gravity. It was a dramatic confirmation, the kind that turns a scientific theory into front-page news and gives the universe a brief moment as a celebrity. Light, which has no ordinary mass in the everyday sense, still follows the curvature of space-time. Gravity is not just pulling material objects, it is shaping the paths available to everything. Another consequence is that time itself is affected by gravity. Clocks run differently in stronger and weaker gravitational fields. A clock closer to a massive object ticks more slowly than a clock farther away. This has been measured, and it matters for technologies like satellite navigation. Your phone's map, in its quiet, practical way, depends on the fact that Einstein was right. This is always a delightful thing to remember when modern life feels ordinary. Somewhere inside the simple act of finding a coffee shop, space-time corrections are doing their tiny mathematical housekeeping. The universe is weird enough to require general relativity and practical enough to help you not miss a turn. If gravity can bend light and alter time, then it is not a small local trick. It is woven into the structure of reality. And if space-time can curve near stars and planets, it can also have a large-scale shape and history. The universe may be flat in one sense, curved in another, expanding in time, filled with matter that slows expansion, and influenced by energy that changes the pace of that expansion. We are now far beyond the simple image of gravity as a downward pull. Down still works in your room. It works very well, especially when you drop toast. But on cosmic scales, gravity is geometry, and geometry can evolve. Still, this does not mean we should discard Newton. Newton's gravity remains an excellent approximation in many situations. Engineers, astronomers, and mission planners still use Newtonian calculations where they are accurate enough, and they usually are. If you want to understand why a ball falls or how a planet moves in a modest gravitational field, Newton serves beautifully. Einstein did not make Newton wrong in the simple sense. He revealed that Newton's theory is a special, approximate case of a deeper theory. This happens often in science. An older idea is not thrown into the bin with yesterday's biscuit crumbs. It is placed inside a wider frame. It becomes part of a larger understanding. For our story, the wider frame is essential. Without Einstein, expansion might be imagined only as matter moving through space. With Einstein, expansion becomes a possible motion of space itself. This is the doorway to the modern answer. Gravity pulls matter together locally, and curved space-time explains that pull more deeply. But the universe as a whole can still expand because its geometry is not fixed. The distances between unbound galaxies can grow as the cosmic scale changes. Gravity affects that expansion, slowing it under some conditions, shaping structures along the way, but not necessarily stopping it. One can think of the universe as having two kinds of behavior happening together. On smaller scales where matter is gathered, gravity wins. It holds galaxies, groups, clusters, planets, moons, and sleeping people in place. On the larger scales, where matter is spread thinly and systems are not bound to one another, the expansion of space becomes the main story. Einstein's theory gives us the language to say this without contradiction. The same theory that describes gravity also describes cosmic expansion. They are not enemies, they are related features of one space-time story. This is where the expanding universe begins to feel less like a strange exception and more like a natural possibility. Once space and time are flexible, a universe that changes is not surprising. In fact, a universe that stayed perfectly static would be the suspicious one. The old clockwork cosmos had a sturdy charm, but Einstein's cosmos is more alive. Not alive like an organism, not thinking or breathing in the ordinary sense, but dynamic, responsive, shaped by its contents and changing across time. It is a universe with a past and a future written into its geometry. And this changing geometry leads directly to the next common misunderstanding. When people hear that the universe is expanding, they often picture an explosion. It is an understandable picture. If things are moving apart, perhaps they were blasted outward from a central point. If distant galaxies are receding, perhaps the Big Bang was like a bomb going off in empty space. But Einstein's stretchy universe points us away from that image. The beginning of expansion was not debris flying into a pre-existing void from a single location. It was the expansion of space everywhere from an earlier hot, dense state. Every region was closer to every other region. There was no ordinary center from which galaxies were launched. The universe did not expand into space. Space itself expanded. That idea takes time to settle. It is not how our daily world behaves. Your bedroom does not expand from every point at once, which is fortunate for furniture arrangements. A cake rises into the air around it. A balloon expands into the room. An explosion sends material into surrounding space. The universe does not fit neatly into any of these. It asks us to imagine that the distances within reality itself were once much smaller and have grown over time. It asks us to give up the search for an edge in the ordinary sense and the search for a centre in the ordinary sense. It asks us to accept that the Big Bang happened not somewhere, but everywhere. Einstein did not begin with that full picture, and he did not hand modern cosmology to the world in finished form. Science rarely arrives wrapped and labelled. It grows through theory, observation, correction, argument, surprise, and the occasional quiet embarrassment of being wrong in an interesting way. But general relativity made the expanding universe physically meaningful. It gave scientists the tools to describe a cosmos whose scale changes. It transformed gravity from a force inside space into a feature of space-time itself. And once that transformation was made, the old question could be asked more clearly. If gravity pulls everything, why is the universe expanding? Because gravity is part of the changing geometry, not a simple command that all distances must shrink. Because local attraction and global expansion can coexist. Because the universe is not a collection of objects in a fixed room, but a room whose walls, floor, and measuring tapes are part of the story. So the next time gravity feels obvious, when your body settles into a mattress or your hand feels the weight of a book, it may be worth remembering that this familiar pull is only the nearby face of something much deeper. Gravity is not just the reason things fall, it is the reason light bends, clocks disagree, planets orbit, black holes form, and the universe can be described as a changing space-time. The same quiet influence that keeps your blanket resting over you also helped reveal that space is not merely emptiness. It has structure, it has history, it can stretch. And once we accept that, we are ready to approach the phrase that causes so much confusion, the Big Bang, not as an explosion in the dark, but as the beginning of a universe whose every distance has been growing ever since. The phrase Big Bang is powerful, memorable, and slightly misleading. It sounds like a noise. It sounds like a burst. It sounds like something happened in one place, in the middle of a great empty darkness, and then matter flew outward like sparks from a firework. You can almost picture it. A tiny bright point appears in a vast black room, suddenly explodes, and sends galaxies racing away in every direction. It is dramatic. It is easy to imagine. It is also not what cosmologists mean. This is one of the most important turns in the story, because many of the confusions about gravity and expansion begin right here. If the Big Bang was an explosion in space, then it is natural to ask what it exploded into, where the centre was, what lies outside the expanding cloud, and why gravity has not pulled all the pieces back toward the middle. Those are reasonable questions for an explosion. If a firework bursts above a field, there is a centre where it went off. There is air around it. There is space into which the fragments move. The fragments slow as they interact with the air and fall under gravity. But early universe was not a firework in a field. It was not a bomb in a room. It was not matter flying through a pre-existing empty stage. The Big Bang was the rapid expansion of space itself from an earlier hot, dense state. That sentence is less cinematic, admittedly. It does not make a satisfying boom. But it is much closer to the real idea. The Big Bang happened everywhere, not at one special location. Every region of the universe that we can observe today was once much closer to every other region. Space was smaller in scale, matter and radiation were hotter and denser. Then the distances between regions grew. The universe expanded, cooled, and changed. Galaxies did not fly out from a central point into empty space. Rather, space between distant regions increased, and matter evolved within that changing space. This is difficult because our ordinary imagination is trained by things inside the universe. We know what it means for steam to expand into a room, or for ink to spread in water, or for a crowd to move outward into a square. In every case, something expands into a surrounding area that already exists. There is an inside and outside. There is a boundary. There is a place where the spreading began. The universe asks us to think differently. When cosmologists say the universe is expanding, they are not talking about material spreading into an outside space. They're talking about the stretching of distances within the universe. The measuring tape itself changes. The map itself grows. A common question is, where did the Big Bang happen? The answer is both simple and strange. It happened here. It happened there. It happened in the direction of the moon, in the direction of the nearest wall, in the direction of every galaxy we can see. It happened everywhere because it was not an event located at one point in space. Space itself was part of the event. The early hot, dense universe was not a small ball sitting somewhere inside a larger emptiness. It was the whole observable universe, and perhaps much more than the observable universe, in a much denser and hotter condition. Every place was closer to every other place. That is why there is no centre of the expansion in the ordinary sense. From Earth, we see distant galaxies receding from us on average. It might be tempting to think this means we are at the centre, but observers in any distant galaxy would see the same general pattern. They too would see faraway galaxies receding. They too could imagine themselves at the centre if they made the same mistake. The expansion has no preferred middle inside space. It is a property of the large-scale universe itself. Every observer, carried along with the cosmic expansion, sees other distant observers moving away as distances grow. The raisin bread image is useful again, though we should handle it gently. Imagine dough with raisins throughout it. As the dough rises, the raisins separate from one another because the dough between them expands. No raisin is the special central raisin. Each raisin sees other raisins moving away. The farther away another raisin is, the more dough lies between them, and the faster the distance between them grows. This gives us a feel for cosmic expansion. But the universe is not actually bread, and galaxies are not raisins floating in dough. The image is only there to loosen the mistaken idea of a central explosion. It helps us see how every location can observe expansion without being the centre of a blast. A balloon covered in dots gives another partial picture. As the balloon inflates, dots on its surface move farther apart. Creatures living on the surface would not find a centre on that surface. Every dot would see other dots receding. The centre of the balloon is not part of the surface world. Again, our universe is not the surface of a balloon in a simple literal way, and it is not necessarily expanding into a higher room around it. But the balloon helps us picture a space whose internal distances increase without requiring a centre within that space. The important point is not the rubber. The important point is that expansion can belong to the geometry of the space itself. Once this becomes clearer, the role of gravity also becomes clearer. In an ordinary explosion, gravity might pull the pieces back toward the centre, if gravity was strong enough, and if the pieces did not escape. But the universe is not pieces moving away from a central blast point. There is no single centre for everything to fall back toward. Gravity acts locally and globally by shaping motion and structure, but it is not pulling all galaxies toward one special cosmic middle. The expansion is not a swarm of fragments fleeing a place. It is the changing scale of space between unbound regions. This does not mean the early universe was calm. It was not calm at all. It was extremely hot, extremely dense, and filled with radiation and particles interacting constantly. But it was not chaotic in the sense of debris flying through empty nothingness from a little spot. The early universe was hot and dense everywhere. When we look far enough into space, we also look back in time, because light takes time to travel. The most ancient light we can observe comes from a time when the universe had cooled enough for light to travel freely. That light now reaches us from every direction as a faint background glow. It is one of the strongest pieces of evidence for the hot early universe. It is not coming from one location where an explosion occurred. It surrounds us from all directions because it is the afterglow of an earlier state that filled space. This background glow is sometimes described as the leftover heat of the Big Bang. That phrase is useful if understood correctly. It does not mean we're seeing the edge of an explosion. It means we're seeing ancient light from a time when the entire observable universe was filled with hot plasma, a state where light could not travel freely for long because it kept scattering off charged particles. As the universe expanded, it cooled. Eventually atoms could form and light could move through space without constantly being scattered. That ancient light has been travelling ever since, stretched by the expansion of space into a faint microwave glow. It is like a baby picture of the universe, though a rather blurry one, and one that took billions of years to arrive. This is where the word beginning becomes delicate. The Big Bang model describes the universe evolving from a hot, dense early state. It does not automatically tell us what happened before that state, or whether before is even the right word. In ordinary life, every event has a before. Before tea, there was a kettle. Before breakfast, there was the mild hope that breakfast would be easy. But when we talk about the earliest moments of the universe, time itself is part of the system we are trying to understand. General relativity allows us to trace the expanding universe backward toward hotter and denser conditions, but at the most extreme early point, our current theories become incomplete. We need a theory that can handle gravity and quantum physics together, and we do not yet have a fully confirmed one. So when someone says the Big Bang was the beginning of everything, that may be true in some sense, but it is more careful to say that the Big Bang model describes the earliest hot dense phase from which our observable universe evolved. It is a theory of cosmic expansion and cooling, not a complete explanation of why there is something rather than nothing, or what if anything preceded the earliest state. Science is comfortable saying what it knows and where its knowledge becomes less secure. This is not weakness, it is how the subject stays honest. The universe is under no obligation to make its first page easy to read. The expansion after the hot early state led to cooling, and cooling allowed complexity. At first, the universe was too hot for atoms to exist as stable structures. Particles and radiation formed a blazing mixture. As space expanded, the temperature dropped. Eventually, simple atomic nuclei could survive. Later, electrons could join nuclei to form atoms. Much later still, gravity gathered gas into the first stars and galaxies. Stars cooked heavier elements in their cores and scattered them through space when they died. Planets formed from enriched material around later generations of stars. Chemistry became more varied. In at least one quiet corner of one galaxy, matter arranged itself into oceans, cells, nervous systems, telescopes, and people who sometimes wonder why their phone charger is never where they left it. Expansion does not prevent structure. It sets the stage on which cooling, gravity, and time allow structure to appear. In fact, without expansion, the universe as we know it would not exist. Expansion allowed the early fire to cool. A universe that remained extremely hot and dense would not form atoms, stars, planets, or anything resembling a calm evening. It would be a very poor environment for sleep science, or sleep, or science. The growth of space changed the conditions. It turned a dense, hot beginning into a cooler universe, where gravity could gather matter into luminous islands. In that sense, expansion and gravity are partners in the story, not simple rivals. Expansion cools and separates. Gravity gathers and builds. Together, across cosmic time, they produce the large-scale universe we observe. Of course, gravity did resist the expansion. Matter attracts matter, and the gravity of all that matter affects how the expansion changes over time. In the early universe, radiation also played a major role. Later, matter became more important in shaping structure. Gravity pulled slightly denser regions inward, allowing galaxies and clusters to grow. If the universe had contained much more matter, gravity might have slowed the expansion more dramatically. If it had contained different ingredients, the future could have been very different. The expansion is not a simple one-time shove. It is an ongoing evolution governed by what the universe contains. This is why cosmologists care so much about the contents of the universe. Ordinary matter, the stuff of atoms, stars, planets, and sleepy human beings, is only part of the total. Dark matter appears to provide additional gravity, helping galaxies and clusters behave as they do. Radiation mattered greatly in the early universe. Dark energy appears to dominate the expansion today on the larger scales. Each ingredient affects the overall cosmic history. To ask why the universe expands is partly to ask what the universe is made of, how it began, and how spacetime responds to its contents. The Big Bang model grew out of both theory and observation. Einstein's general relativity made dynamic universes possible. Friedman and Lemaitre showed that the equations could describe expansion. Observers found that distant galaxies showed redshift, suggesting that the universe was indeed expanding. Later, the discovery of the cosmic background radiation strongly supported the idea of a hot, dense early state. Measurements of light elements also matched the expectation that the early universe had once been hot enough for nuclear processes to occur. The picture became stronger not because it was dramatic, but because many different clues pointed in the same direction. The word redshift deserves a gentle explanation, because it is central to how we know expansion is happening. Light can be stretched. When light from a distant galaxy travels through expanding space, its wavelength becomes longer. Longer visible wavelengths are toward the red side of the spectrum, so astronomers call this a redshift. Though for very distant objects the light may be stretched beyond visible red altogether. The greater the distance in general, the more the light has been stretched by the expansion during its journey. This pattern is one of the key signs that space itself has been growing over cosmic time. Again, this is not the same as galaxies simply racing through space like thrown stones. Galaxies can have local motions due to gravity, and those motions matter nearby. But over very large distances, the overall redshift pattern points to the expansion of space. A galaxy far away is not necessarily moving through space at an enormous speed in the ordinary local sense. Rather, the space between us and that galaxy has grown while the light travelled. This distinction is subtle, but it prevents many misunderstandings. Space is not a substance dragging galaxies along, but the geometry that defines distance is changing. One consequence is that very distant galaxies can recede from us faster than light, in a certain cosmological sense, without breaking the rule that nothing moves through local space faster than light. This sounds alarming at first, like physics has left a door open and the furniture has escaped. But the rule from relativity applies to motion through space locally. Cosmic recession due to the expansion of space over vast distances is different. No galaxy is locally overtaking a light beam in its own neighbourhood. The distance between us and the galaxy increases because the space between grows. This is another reason the explosion picture fails. In a normal explosion, fragments moving faster than light would be forbidden. In cosmic expansion, the issue is the growth of distance across large-scale space-time. The observable universe has a limit because light has had only a finite time to reach us since the early hot, dense phase. Beyond the farthest we can see, there may be much more universe, perhaps vastly more, but its light has not reached us. The observable universe is not the whole universe necessarily. It is the region from which light has had time to arrive. This distinction matters. When we say the early observable universe was once hot and dense, we do not mean the whole universe was necessarily a tiny dot in some larger space. We mean the region we can now observe was once compressed into a much smaller volume, with every part much closer together. The whole universe may be infinite, or it may have a finite shape without an edge. We do not yet know for certain. That last phrase, without an edge, can feel especially odd. We're used to finite things having boundaries. A table has edges, a room has walls. A biscuit has a boundary, at least until someone eats it with suspicious speed. But geometry allows more possibilities. The surface of Earth is finite in area but has no edge. You can travel around it and never reach a boundary where the surface simply stops, though you may reach an airport, which can feel similar after a long delay. The universe could, in principle, have a finite volume without an edge, depending on its overall geometry, or it could be infinite. Current observations suggest that the part we can see is very close to spatially flat, but this does not settle every question about the whole. What matters for our present question is that expansion does not require an outside and does not require a centre. It is enough for distances within space to change. The Big Bang was not matter exploding into space. It was the early expansion of space and everything in it. From that beginning, the universe cooled, matter gathered, light travelled, stars formed, and structure emerged. Gravity was active throughout, but it did not need to pull everything toward one centre, because there was no central point of explosion. Instead, gravity worked within the expanding universe, strengthening dense regions and shaping the cosmic web. There is something calming about clearing away the false explosion image. It does not make the universe smaller or less strange. If anything, it makes it stranger in a more accurate way. A firework is dramatic but familiar. An expanding space-time with no central point, filled everywhere in the past with hot dense matter and radiation, cooling into galaxies and stars, is far more profound. It tells us that every direction in the sky is a direction into the history of the cosmos. It tells us that the atoms in our bodies belong to a universe whose earlier state was unimaginably hot and dense. It tells us that the night sky is not just a place where distant things are, but a record of changing space and time. And it helps answer the original question with more care. Gravity pulls, but the expansion did not begin as an ordinary explosion that gravity should simply reverse toward a centre. The universe began, as far as our best-tested model tells us, in a hot, dense state where space itself was expanding. Gravity influenced that expansion and shaped the matter within it. It did not stop all expansion because the cosmic history depends on the overall contents and conditions of the universe, not on the simple idea that attraction must always lead to collapse. In some regions, gravity gathered matter successfully. In the largest unbound regions, distances continued to grow. The early universe was also incredibly smooth on large scales, with only tiny density differences. Those tiny differences were enough for gravity to begin its long work. A slightly denser patch attracted more matter. Over time, it became a seed for galaxies or clusters. Less dense regions became emptier, forming great cosmic voids. Expansion stretched the overall universe, while gravity amplified the unevenness. It is not unlike watching a pattern develop in slow motion across an enormous fabric. Some threads draw together. Some spaces widen. The whole cloth changes, but local knots still form. As the universe expanded further, the balance between its ingredients shifted. Radiation thinned and lost energy as light stretched. Matter became the dominant gravitational influence for a long era. Stars and galaxies flourished. Much later, dark energy became increasingly important in the large-scale expansion. That later acceleration is a separate surprise, one we will come to carefully. For now, the main task is to hold the correct picture in mind. The Big Bang was not a central blast. The universe has no known centre of expansion. Space itself has been expanding, and gravity has been shaping matter within that expansion. So when we imagine the earliest universe, we should not picture ourselves outside it, watching a glowing ball appear in darkness. There is no outside viewing platform in the model, no comfortable cosmic balcony with a safety rail, and a small sign saying, "Please do not lean over the beginning of time." We are inside the universe, and every observation we make is from within it. Our models describe how distances, temperatures, densities, and structures changed over time. We reconstruct the past by reading the evidence carried by light, matter, and the large-scale pattern of galaxies. It is a detective story told from inside the scene itself. This inside perspective is important. It keeps us from asking the wrong version of good questions. Instead of asking where the Big Bang exploded, we ask how space evolved from a hot, dense state. Instead of asking what direction galaxies are flying away from the centre, we ask how distances between galaxies change with time. Instead of asking why gravity has not pulled the fragments back to the explosion point, we ask how gravity, matter, radiation, dark matter, and dark energy together determine the expansion history. The questions become more precise, and the answers become less like science fiction and more like cosmology. And with that clearer picture, we can return to the tug-of-war that sits at the centre of tonight's subject. Expansion increases distances across the universe. Gravity pulls matter together and slows separation where it can. Sometimes gravity wins locally, building galaxies, clusters, and eventually the structures that make stars and planets possible. Sometimes expansion wins globally, carrying unbound regions farther apart. The history of the universe is not one force simply defeating another in a single dramatic contest. It is a changing balance, a long negotiation between the contents of the cosmos and the evolving geometry of space. To understand why distant galaxies keep receding while galaxies themselves hold together, we need to look more closely at that balance and at the quiet cosmic contest between the inward pull of gravity and the outward growth of space. Picture, for a moment, a very patient contest taking place across the entire universe. On one side is gravity, the old familiar pull, the force that gathers dust into planets, gas into stars, stars into galaxies, and galaxies into clusters. Gravity is persistent. It does not shout. It does not hurry. It simply keeps tugging second after second, century after century, as if the cosmos were full of loose threads, and gravity had decided to spend eternity drawing them together. On the other side is expansion, not a force in quite the ordinary sense, not a wind blowing galaxies apart, but the steady growth of space between regions that are not bound together. Expansion does not pick things up and throw them. It increases the distance between faraway places, it widens the gaps, it stretches the cosmic map while gravity tries, wherever it can, to fold matter into neighbourhoods. This is the tug-of-war that sits at the heart of the question. If gravity pulls, why does the universe expand? Because gravity and expansion are not doing the same job in the same way at the same scale. Gravity gathers matter into structures. Expansion changes the distances between unbound structures on the larger scales. Sometimes gravity wins, sometimes expansion wins. Often they are both active at once, shaping the universe into something neither one would have made alone. The phrase tug-of-war is useful, though a little playful. In a normal tug-of-war, two teams pull on opposite ends of a rope, ideally without anyone falling into the mud, although that is often the best part for spectators. But cosmic expansion is not exactly pulling outward against gravity. There is no rope stretched across the universe with gravity holding one end and expansion holding the other. The contest is more subtle. Gravity acts through matter and energy, curving space-time and drawing matter into denser regions. Expansion is the changing scale of space itself. The question is whether gravity, acting through the mass and energy of the universe, can slow that expansion enough to halt it, reverse it, or merely shape it along the way. For much of modern cosmology, scientists thought of the universe's fate in these terms. The universe was expanding, yes, but surely gravity should be slowing that expansion. The question was how much? Imagine throwing a ball upward. As it rises, gravity pulls it back. If you throw it gently, it slows, stops, and falls. Throw it harder, and it goes higher before returning. Throw it fast enough, and it escapes Earth completely. This everyday picture is not exactly the universe, because cosmic expansion is not a ball flying through air. but it gives us a useful feeling for the issue. Expansion can continue even while gravity slows it. The final result depends on how strong the expansion is and how much gravitational pull exists in the universe. If the universe had contained enough matter, gravity might have eventually brought the expansion to a stop. After that, the universe could have begun contracting, with galaxies drawing closer over immense stretches of time, the cosmic background growing warmer, and all space moving toward a dense final state. This idea was sometimes called a big crunch, which sounds like either a cosmological fate or an unfortunate breakfast cereal. It was a serious possibility. In a matter-rich universe, gravity could, in principle, win the largest battle. If the universe contained too little matter, expansion would continue forever. Gravity would still slow it, but never enough to stop it. Distant galaxies would keep receding. The universe would grow colder and more spread out over time. Stars would form for a while, burn, fade, and eventually the cosmos would become darker and thinner. This was another possible fate. A universe with insufficient gravity would expand without turning back. There was also a delicate middle possibility, where the universe had just enough matter for expansion to slow forever, approaching a halt but never quite reaching collapse. It is the kind of balance physicists often find appealing, because it feels neat, like a pencil standing perfectly on its point, at least until reality breathes on it. For decades, cosmologists tried to measure the expansion rate and the amount of matter in the universe to determine which future awaited everything. Would gravity win? Would expansion win? Would the universe balance on the edge? The first surprise was that most of the matter involved in gravity was not the ordinary matter we know. Stars, gas, dust, planets, and people are made of atoms, and atoms are very important to us, for obvious personal reasons. But when astronomers studied galaxies and galaxy clusters, they found that visible matter did not provide enough gravity to explain what they saw. Galaxies rotated in ways that suggested much more mass was present than could be accounted for by stars and gas alone. Clusters of galaxies held together more strongly than visible matter allowed. Light from distant objects bent around massive clusters more than expected from the glowing matter. Something unseen seemed to be adding gravity. This unseen ingredient is called dark matter. It does not shine, absorb, or reflect light in a normal detectable way, but it appears to have mass and therefore gravity. It is not dark because it is sinister, though the name does make it sound like it should live in a castle and wear a cloak. It is dark because we do not see it directly. We infer it from its gravitational effects. Dark matter became essential to understanding how cosmic structures formed. Without it, galaxies would have had a much harder time forming as early and as strongly as they did. Ordinary matter interacted with radiation in the early universe, but dark matter could begin gathering under gravity in a different way, helping create the gravitational scaffolding into which ordinary matter later fell. In the tug-of-war between gravity and expansion, dark matter strengthens gravity's side. It helps matter clump. It deepens gravitational wells. It gives galaxies extra holding power and helps clusters form. If the universe contained only the matter we can see, gravity would be much weaker on cosmic scales. With dark matter, the cosmic web becomes possible in the way we observe it. Filaments of matter stretch across huge distances. Galaxy clusters form at intersections. Great voids open between them. The universe becomes a vast sponge-like structure, though much prettier than the sponge near the sink and considerably less in need of replacing. The cosmic web is one of the clearest signs that gravity has been hard at work inside the expanding universe. Expansion tries to carry regions apart, but gravity draws matter toward denser areas. The early universe was not perfectly smooth. It had tiny variations in density, slight differences from place to place. They were very small, but gravity is patient. A region with a little more matter had a slightly stronger pull. It attracted more matter, becoming denser. As it became denser, it attracted still more. Over millions and billions of years, tiny differences grew into stars, galaxies, clusters, and filaments. A barely noticeable wrinkle in the early universe became the cosmic architecture we see today. This is why the universe is not a smooth mist of particles evenly thinning out everywhere. If expansion had acted alone, with no gravity, matter would have spread and cooled without forming the rich structures we know. If gravity had acted alone in a static universe, matter might have collapsed more directly into dense clumps. But together, expansion and gravity created a more interesting history. Expansion cooled the universe and increased distances. Gravity amplified small irregularities and built structure. The result is not simple spreading and not simple collapse, but a universe filled with islands, rivers, walls, and voids of matter. This balance also explains why some objects are moving toward us in an expanding universe. The Andromeda Galaxy, our large galactic neighbour, is approaching the Milky Way. This sometimes confuses people. If the universe is expanding, why is Andromeda coming closer? The answer is that Andromeda and the Milky Way are close enough for local gravity to dominate over cosmic expansion. We are part of a gravitationally bound group of galaxies. Within this group, galaxies move according to their mutual gravitational pulls, not according to the simple large-scale expansion pattern. Andromeda is not disobeying cosmology, it is obeying local gravity. The same is true inside galaxy clusters. The galaxies within a cluster are bound together by gravity, including the gravity of dark matter. They orbit, interact, merge, and sometimes pass through one another in slow, majestic collisions. The cluster as a whole may be separated from other distant clusters by expanding space, but inside the cluster, gravity rules. In your own body, electromagnetic forces hold atoms and molecules together, while Earth's gravity holds you to the planet. Cosmic expansion is far too weak to pull you apart. You may feel stretched at the end of a long day, but that is not the Hubble expansion. That is probably posture, stress, or an ambitious chair. A helpful distinction is between bound and unbound systems. A bound system is one where gravity, or another force, holds the parts together strongly enough that they do not simply join the general cosmic expansion. Earth is bound to the Sun. The Moon is bound to Earth. The stars of the Milky Way are bound within the galaxy. The galaxies of our local group are bound together. But distant galaxy clusters, separated by vast stretches of space, may not be bound to one another. Between them, expansion can grow the distance over time. The universe expands not by tearing apart everything within it, but by increasing distances where no local binding is strong enough to resist the overall change. This means there is no need to imagine expansion working like a hidden pressure inside every object. It is not trying to inflate your furniture. It is not making atoms larger. It is not quietly increasing the gap between your teeth while you sleep, which is a relief. The expansion of the universe is a large-scale behaviour. On small scales, forces easily overcome it. The electromagnetic forces inside matter are enormously stronger than the effect of cosmic expansion over the size of an object. Gravity inside bound astronomical systems also dominates. Only at immense distances between unbound structures does expansion become the main description. There is a subtle point here that is worth approaching slowly. When we say gravity slows expansion, we do not mean gravity is reaching into space like a brake pad rubbing against a wheel. Instead, the contents of the universe determine how the geometry of space changes over time. Matter and energy affect spacetime, and spacetime's evolution is what we observe as expansion. In a universe filled mostly with matter, gravity tends to make the expansion slow down. The matter pulls on itself. The geometry responds. The scale grows more slowly than it would without that attractive influence. This is not a mechanical break in the ordinary sense, but the outcome is similar enough for a bedtime explanation. Gravity resists the growth of distance, For a long time it seemed obvious that the expansion of the universe should be slowing. After all, matter attracts, dark matter attracts, galaxies attract, clusters attract. Even if expansion continued forever, it should at least lose speed over time. This expectation was so reasonable that when astronomers set out to measure cosmic history, many were trying to find out how much the expansion had slowed. The idea that it might be speeding up was not the natural guess. It was not what gravity led anyone to expect. If you throw a ball upward and it accelerates away from Earth instead of slowing down, you do not calmly nod and say, "Yes, that seems tidy." You check for rockets. Before we arrive at that surprise, though, it helps to understand how one might measure the tug-of-war. Astronomers need to know distances and recession speeds. Distances in cosmology are difficult. You cannot stretch a tape measure to a galaxy, and even if you could, someone would trip over it near Mars. Instead, astronomers use objects whose brightness can be understood. If you know how bright something truly is, and you measure how dim it appears, you can estimate how far away it is. Certain stars and certain supernova explosions serve as cosmic distance markers. They are not perfect, but they can be calibrated carefully. Alongside distance, astronomers measure redshift, the stretching of light, which tells us how much the universe has expanded during the light's journey. By comparing distances and redshift across many objects, scientists reconstruct the expansion history of the universe. They're not merely asking how fast things are receding now. They're asking how the expansion rate has changed over billions of years. This is like looking at tree rings to understand past seasons, except the tree is the universe, the rings are ancient light, and the gardener has been unavailable since the beginning of time. The farther away an object is, the older the light we see from it. Looking deep into space is looking back into cosmic history. We can compare different eras by observing objects at different distances. In a universe where gravity alone slows expansion, very distant supernovae should appear with a certain pattern of brightness and redshift. They should tell us that expansion was faster in the past and has been slowing down over time. The universe would be coasting outward under the influence of its original expansion, while gravity tugged it back. This was the expected tug-of-war. Expansion moving forward, gravity reducing the pace. At smaller scales, we can see gravity's victories clearly. Stars form because gas collapses under gravity. A cloud of gas, if cool and dense enough, can begin to contract. As it contracts, parts of it fragment into denser clumps. Eventually, the pressure and temperature in the core of a clump become high enough for nuclear fusion to begin, and a star is born. That star may gather planets from a disk of material around it. Gravity is the sculptor. It takes diffuse matter and makes centers. It turns cloud into flame. It turns dust into worlds. Without gravity, the universe would have no stars to warm planets, no galaxies to host them, no heavy elements made in stellar furnaces and scattered by stellar deaths. Gravity is the reason the universe has places, but gravity is not always neat. It can create order from one point of view and violence from another. Galaxies collide and merge, stars explode, black holes form, clusters swallow smaller groups. Matter falls inward, heats up, radiates, and sometimes vanishes behind horizons from which light cannot return. Gravity builds, but it builds with the manners of a very determined builder who occasionally knocks through the wrong wall. Expansion, by contrast, creates room. It lowers the average density, it stretches light, it cools the universe, it makes the great distances greater. Together, they produce a cosmos where local drama unfolds inside a background that keeps widening. This combination can feel contradictory because human language tends to prefer one main action at a time. Is the universe expanding or collapsing? Is gravity winning or losing? But nature often answers, yes, depending where you look. A collapsing gas cloud can form a star inside an expanding universe. A galaxy cluster can remain bound while the distance to another cluster grows. The universe can be expanding overall while some regions fall inward. There is no contradiction because the statements refer to different scales and systems. Think of a loaf rising again, but now imagine that some raisins are sticky and clump together as the dough expands. Nearby raisins can form little groups, while the groups themselves move farther apart as the dough rises. The clumps are local gravity. The rising dough is expansion. The loaf is still not the universe, and we should not ask what bakery it came from, but the analogy does useful work. It shows how local gathering and overall expansion can occur together. The universe is full of gravitationally bound clumps embedded in an expanding background. The history of expansion also changes over time because the ingredients thin differently. Matter becomes more spread out as space grows. Radiation not only becomes more spread out, but its light is stretched, so it loses energy in a cosmological sense. Dark energy, in the simplest model, behaves differently. Its density does not dilute in the same way as matter as space expands. That difference becomes crucial later. In the earlier universe, matter had a stronger role in slowing expansion and building structure. In the more recent universe, dark energy appears to dominate the large-scale expansion. This shift is one of the reasons the cosmic tug-of-war has not had the same character forever. For now, imagine the universe after the early hot phase, expanding and cooling. Matter is present, both ordinary and dark. Gravity begins drawing matter into denser regions. Expansion continues, increasing the overall scale. At first, radiation is important. Later, matter becomes more influential. Structures grow, galaxies form, clusters assemble. During this long period, gravity is doing exactly what our intuition expects. It slows the expansion compared with what it might have been, and it gathers matter into cosmic architecture. If the story had ended there, the universe would be easier to explain. It would still be immense and difficult, but it would have a certain classical neatness. The universe expands because it began expanding, and gravity slows it while building structure. Depending on the amount of matter, expansion either continues forever or eventually reverses. That was a tidy menu of futures. Unfortunately, the universe seems to have ordered something else. Observations in the late 20th century showed that distant supernovae were dimmer than expected in a way that suggested the expansion has been accelerating, not merely continuing, not merely slowing less than expected, accelerating. The gap between distant unbound regions is growing at an increasing rate. Gravity still pulls, matter still clumps, galaxies still merge locally. But on the larger scales, something associated with empty space itself appears to be driving accelerated expansion. This is the point where the tug-of-war gains a third character. Gravity and expansion were already subtle. Now dark energy enters, quietly but decisively. If dark energy behaves like a property of space, then as space expands, more space means more of this effect. Matter thins out as the universe grows, but dark energy does not fade in the same way, at least according to the simplest current picture. Over time, its influence becomes more important. Gravity had a stronger grip in the past when matter was denser. But as expansion spread matter thinner, dark energy came to dominate the cosmic scale. The result is accelerated expansion. This does not mean galaxies are being ripped apart now. Bound systems remain bound. The Milky Way is not expanding internally. The solar system is not swelling. Earth is not gradually losing the moon because of dark energy. Local gravity and other forces are still far stronger on these scales. The acceleration matters mainly across the enormous distances between galaxy clusters and superclusters that are not gravitationally bound together. It affects the future visibility of the universe. Over immense time, distant galaxies may recede so far and so fast that their light can no longer reach us. The cosmic horizon changes. The observable universe of far future astronomers may become lonelier. There is something quietly sad about that, though not immediate. We live at a time when the universe is old enough for stars and planets, but not so old that all distant galaxies have disappeared beyond view. The sky still contains evidence of the wider cosmos. The cosmic background still reaches us. The patterns of galaxies can still be mapped. We are, in a sense, living during an era when the universe can study itself. That is a strange privilege for a species that also spends considerable time losing keys. The tug-of-war, then, is not a single contest with a simple winner. In dense local regions, gravity wins. It forms and holds structures. Across vast unbound distances, expansion carries regions apart. In the early and middle history of the universe, gravity slowed the expansion and built the cosmic web. In the more recent universe, dark energy appears to have tipped the large-scale behavior toward acceleration. Gravity has not stopped working. It has simply become less dominant over the overall expansion as matter has thinned and dark energy has become the leading influence. If this feels like a compromise answer, that is because the universe is full of compromises. It is expanding, but not everything expands. Gravity pulls, but not every pull leads to collapse. The Big Bang was hot and dense, but not an explosion into space. Space stretches, but not like rubber in every situation. Dark matter gravitates, but does not shine. Dark energy accelerates expansion, but we do not yet know exactly what it is. The correct picture is more layered than the first question suggests, and that is what makes it worth asking. One of the most helpful things to remember is that gravity is a builder of contrast. It takes small differences and makes them larger. A slightly dense region becomes denser. A slightly empty region becomes emptier as matter flows away into surrounding structures. Expansion, meanwhile, increases the overall scale and can make empty regions vast. The cosmic web is the combined result. Matter drains from voids into filaments and clusters. Voids expand and become emptier. Clusters grow but remain localized. From far away, the universe looks like a network of glowing threads around dark open spaces. Gravity made the threads. Expansion widened the spaces. In daily life, we rarely meet anything like this. We see gravity as a downward pull and expansion as something balloons do at birthday parties. The universe uses the same words but at a scale where they gain new meanings. A galaxy cluster is not a party balloon. Spacetime is not dough. Gravity is not a hand. Dark energy is not ordinary fuel. The analogies help us begin, but the real answer is in the observations and the theory that connects them. The universe expands because its geometry evolves. Gravity resists and shapes that evolution. Matter gathers where gravity can bind it. The largest distances grow because the whole cosmic scale changes, and today that growth is accelerating. This may actually make the original question more beautiful. If gravity simply lost everywhere, there would be no galaxies. If expansion simply lost everywhere, the universe might have collapsed or become a very different place. We exist because the contest allowed both space and structure. Expansion gave the universe room and cooling. Gravity gave it stars and planets. The balance was not designed for us, at least not in any scientific explanation, but we are one of its outcomes. A universe that only expanded smoothly might be empty and dark. A universe that collapsed too quickly might never form long-lived stars. Our existence depends on a history in which gravity and expansion each had their era, their scale, and their influence. So when you feel gravity now, as a soft heaviness in your body, or the reassuring pressure of a blanket, you're feeling the local champion. Gravity is one here. It gathered the matter that made Earth. It holds the atmosphere close. It keeps oceans wrapped around the planet. It gives your body weight, and your room a dependable floor. But far beyond the Milky Way, between clusters separated by gulfs of space so large that light itself spends millions and billions of years crossing them, expansion is writing the larger story. The distances grow, the light stretches, the cosmic web slowly changes. The universe is not flying apart in a careless way, and it is not collapsing into one heap. It is doing something more interesting. It is expanding while gravity gathers, cooling while stars burn, thinning while structures deepen, accelerating while local systems remain bound. The tug-of-war is not noise or contradiction. It is the mechanism behind the universe we see. And just as we begin to understand that gravity and expansion can coexist, we come to the strangest part of all, the discovery that the larger scale expansion is not merely surviving gravity's pull, but speeding up, as though the emptiest parts of the cosmos have their own quiet influence, one that scientists call dark energy. Dark energy is one of those names that sounds as if science briefly handed the naming job to a fantasy novelist. It sounds dramatic, almost suspicious, as though the universe has a hidden villain somewhere beyond the galaxies, wearing a velvet cloak and quietly pushing everything apart. But dark energy is not dark in that sense. It is not evil, not smoky, not a mysterious substance you could scoop into a jar, label and store beside the tea bags. It is called dark because we do not see it directly, and energy because whatever it is, it affects the expansion of the universe. It is one of the deepest puzzles in modern cosmology, and it entered the story not because scientists were looking for something dramatic, but because the universe refused to behave in the way gravity seemed to predict. For a long time, the sensible expectation was simple enough. The universe was expanding, but gravity should be slowing that expansion down. Galaxies pull on galaxies, clusters pull on clusters. Matter, including dark matter, adds its attraction to the great cosmic account. The universe might keep expanding forever, or it might one day slow to a stop and collapse, but either way the expansion should be losing speed. That was the reasonable idea. Gravity is attractive. Matter pulls inward. An expanding universe filled with matter should not accelerate outward unless something else is involved. It would be like tossing a ball into the air and watching it not only continue upward, but begin rising faster, as if the sky had quietly installed an invisible lift. So astronomers set out to measure how much the expansion was slowing. The aim was not originally to discover a strange new cosmic ingredient. It was to settle the question of the universe's fate. Would gravity eventually win? Would expansion continue forever? How much matter was there? How strong was the braking effect? These were careful, serious questions, the sort that require patient observations, well-calibrated instruments, and probably more late nights than anyone admits in the official papers. The key was to look at very distant objects, because looking far away in space means looking back in time. Light takes time to travel, so a faraway galaxy is seen as it was when its light began the journey toward us. By measuring many objects at different distances, astronomers could reconstruct how the expansion rate had changed across cosmic history. One of the most useful tools for this work was a special kind of exploding star known as a Type 1 supernova. These explosions happen in systems involving white dwarf stars, and under the right conditions they can reach a predictable brightness. That makes them valuable as distance markers. If you know how bright something truly is, and then measure how faint it appears, you can estimate how far away it must be. It is a little like seeing a lamp across a foggy field. If you know the lamp's actual strength, its apparent dimness tells you something about the distance. Of course, galaxies are not fields, supernovae are not bedside lamps, and the universe is not kind enough to come with tidy labels saying actual brightness printed underneath each star. But with careful calibration, these supernovae became some of the best tools for measuring cosmic distances. Astronomers compared those distances with redshift, the stretching of light caused by cosmic expansion. They expected to find evidence that the expansion had slowed over time. Instead, the distant supernovae appeared dimmer than expected. That meant they were farther away than they should have been in a universe whose expansion was only slowing under gravity. The best explanation was startling. The expansion of the universe had been slower in the past than it is now. In other words, at some point in cosmic history, the expansion began to accelerate. This was not a small adjustment, like discovering that the sofa is slightly farther from the wall than you thought. It changed the expected fate of the universe. It meant that gravity, while still vital and powerful locally, was not the only major influence on the larger scale behaviour of space. Something else seemed to be causing the expansion to speed up. Scientists gave that unknown cause the name dark energy. The word energy here can be a little slippery. In daily life, energy is something we associate with batteries, food, sunlight, exercise, or the alarming enthusiasm of a child who has eaten too much sugar. Dark energy is not energy in that everyday sense. It is not a fuel burning in the void. It is not stored in galaxies like petrol in a tank. It is a name for whatever causes the observed acceleration of cosmic expansion. The simplest possibility is that dark energy is a property of space itself. Empty space may not be truly empty. It may have a kind of built-in energy that affects how space-time evolves. This idea is connected to the cosmological constant, the same kind of term Einstein once introduced to keep the universe static, though its modern role is very different. Instead of balancing gravity to freeze the cosmos, it can drive acceleration. That little historical twist is almost too neat. Einstein added a term because he wanted a static universe. Later, after expansion was discovered, the term seemed unnecessary and perhaps regrettable. Then, decades later, observation suggested that something very much like it might be needed after all, not to stop expansion, but to explain why it speeds up. Science sometimes has the manners of a long conversation in which an idea leaves the room, returns wearing a different hat, and insists it was relevant all along. If dark energy is a property of space, then it behaves in a very unusual way. Matter becomes more diluted as the universe expands. Imagine galaxies spread through a growing volume. As space grows, the average density of matter drops. Radiation also dilutes, and its light stretches, losing energy in a cosmological sense. But dark energy, in the simplest model, does not thin out in the same way. The density of dark energy remains roughly constant as space expands. That means that as more space comes into the cosmic picture, the total influence of dark energy grows. Matter becomes less dominant over time, while dark energy becomes more important. Eventually, it takes over the large-scale expansion. This helps explain why the universe did not appear to accelerate strongly from the very beginning. In the early universe, matter and radiation were much denser. Gravity from matter had a stronger effect on the expansion, slowing it and helping structure form. Galaxies and clusters could grow because matter was close enough, and gravity had enough time and influence to gather it. Dark energy may have been present, but it was not the dominant player. Later, as the universe expanded and matter thinned out, the constant presence of dark energy became more significant. The cosmic balance shifted. The expansion, once slowed by gravity, began to speed up. The word gentle in gentle acceleration matters. The universe is not exploding faster in some violent local way. Your room is not being pulled apart. The moon is not being snatched from Earth by dark energy. The Milky Way is not swelling like a loaf in an oven. Bound systems remain bound because local gravity and other forces are much stronger than the effect of dark energy at those scales. Dark energy shows itself across immense distances, between galaxy clusters, and across the large-scale structure of the cosmos. Its influence is not a gust of wind. It is a slow, subtle, cumulative effect on the expansion of space itself. That is why dark energy can be so hard to imagine. It does not announce itself in the way a falling object does. You cannot place a cup on a table and watch dark energy push it sideways. You cannot feel it under your feet. It does not heat your hands or rattle your windows. Its evidence comes from the largest measurements we can make, from the brightness of distant supernova, the pattern of galaxies, the ancient background light left from the early universe, and the way all these clues fit together in a model of cosmic history. Dark energy is not sensed directly. It is inferred from the universe's long-term behaviour. This makes it both scientific and deeply mysterious. Scientific because the inference comes from evidence, measurement, and models that can be tested against observations. Mysterious because we still do not know what dark energy truly is. The simplest explanation, the cosmological constant, works very well in many ways. It says that empty space has a constant energy density and that this drives acceleration. But when physicists try to connect this idea with quantum theory, problems arise. The predicted value from simple approaches can be wildly different from what the universe appears to show. Wildly is a gentle word here. It is the kind of mismatch that makes physicists stare quietly at blackboards for a long time, perhaps reaching for another biscuit with the gravity of someone who has seen too much. Other ideas have been proposed. Maybe dark energy is not constant but changes over time. Maybe it's a dynamic field spread through space, slowly evolving across cosmic history. Maybe our theory of gravity needs modification on the larger scales, so what we call dark energy is really a sign that general relativity is incomplete when applied to the universe as a whole. Maybe there is some deeper connection between quantum physics, space-time, and vacuum energy that we do not yet understand. Scientists explore these possibilities carefully, because when a mystery is this large, it is unwise to become too attached to the first tidy answer. The universe has a habit of rewarding patience and embarrassing overconfidence. Still, any alternative must explain the observations at least as well as the current model. This is an important point. Dark energy is not just a word used to hide ignorance. It is a placeholder for a real observed effect. The universe's expansion history, the cosmic background radiation, and the large-scale distribution of galaxies all point to a cosmos where something like dark energy plays a major role today. The exact nature is unknown, but the need for an explanation is not casual. It is written across the data. The mystery is not whether the universe is accelerating, at least under our best current interpretation. The mystery is why. There is a strange humility in that. We understand enough to say that most of the universe's present energy budget appears to be in a form unlike ordinary matter, unlike dark matter, unlike radiation. Yet we do not understand its nature. Everything familiar, stars, planets, gas clouds, oceans, mountains, books, blankets, sleepy listeners, makes up only a small fraction of the cosmic total. Dark matter adds much more gravitational structure, but even that is not the dominant component today. Dark energy appears to make up the largest share. The universe, it turns out, is mostly made of things we cannot directly see and do not fully understand. It is a magnificent blow to human smugness, delivered very politely by the sky. And yet, this does not make our knowledge meaningless. Quite the opposite. It means our tools have become sensitive enough to detect the outline of what we do not know. That is progress. Early astronomers tracked planets against stars. Newton revealed the gravitational law connecting Earth and the heavens. Einstein revealed space-time as dynamic. Observers discovered galaxies beyond our own and the expansion of the universe. Later measurements revealed the cosmic background radiation, dark matter, and accelerated expansion. Each step widened the map. Each step also revealed new blank spaces. Science is not the replacement of mystery with boredom. It is the transformation of vague mystery into precise mystery, which is much more useful and often much stranger. The acceleration caused by dark energy also changes the long-term future. If dark energy remains constant, distant unbound galaxies will recede faster and faster. Over vast timescales, many galaxies beyond our local group may become impossible to observe, not because they vanish, but because the light they emit will never reach us. Space between us and them will expand too much for their signals to cross the growing distance. Future astronomers, if any exist in the far future within our merged local galaxy, may see a much emptier sky. The evidence for the wider expanding universe may become harder to find. The cosmic background will be stretched and cooled to near undetectability. Distant galaxies will slip beyond the horizon. The universe will not end in a dramatic curtain drop. At least in this scenario, it will become increasingly quiet, wide, and cold. That future is sometimes called heat death, though the phrase sounds more theatrical than the process. It does not mean everything suddenly catches fire. It means that over immense spans of time, usable energy becomes less available, stars burn out, matter changes form, and the universe approaches a state of thin, cold, quiet equilibrium. Dark energy makes that future more isolated, because accelerating expansion separates unbound regions more and more. Our local group of galaxies may remain together, eventually merging into one large galaxy, while distant galaxies fade from view. The cosmos becomes a collection of islands losing sight of one another. This may feel melancholy, but it is not a concern for tomorrow morning. It is a story of timescales so vast that ordinary words nearly give up. The sun will live for billions more years. Stars will continue forming for a long time, though at a declining rate. The cosmic future unfolds on scales far beyond human planning, beyond calendars, beyond civilizations as we know them. It is not something to worry about while setting an alarm. It is something to contemplate gently, like a distant shore seen through fog. It reminds us that the universe has a history, and that history has direction. Dark energy also helps us understand why the question tonight is not solved by saying gravity pulls everything. Gravity does pull. It pulls matter into galaxies, holds clusters together, bends light, forms stars, and shapes the cosmic web. But the expansion of the universe is governed by the full contents of the cosmos and by the behavior of space-time itself. If dark energy is a property of space, then it acts not by overpowering gravity in your room, but by influencing the large-scale rate at which space expands. Gravity remains the great local architect. Dark energy is the quiet, large-scale influence changing the pace of the whole map. A simple way to hold the picture is this. In the early universe, matter and radiation were dense, and gravity had a strong role in slowing expansion and forming structures. As the universe grew, matter thinned. Gravity still bound the structures that had formed and continued to shape local regions, but it became less able to control the overall expansion. Dark energy, remaining steady in density, became dominant. The expansion began accelerating. This is not gravity failing. It is the cosmic balance changing over time. The word balance is useful, but even it can mislead if we imagine a scale with two neat pans. The universe is more like a history of changing conditions. Different ingredients dominate at different times. Radiation dominated very early. Matter dominated later. Dark energy dominates now. Each era leaves marks. The early radiation era shaped the background light and the seeds of structure. The matter era allowed galaxies and clusters to grow. The dark energy era controls the future expansion on the larger scales. We live after the universe has formed rich structure, but after dark energy has begun guiding the long-term expansion. We arrived late enough for planets, but early enough to see the wider cosmos. That timing is quite remarkable, though the universe has not asked us to take it personally. There is also a quiet connection between dark energy and emptiness. We usually think of empty space as nothing, a blank, a gap, the part between things. But modern physics has repeatedly taught us that emptiness is not simple. Fields can exist throughout space. Quantum theory suggests that even vacuum has structure. General relativity tells us that space-time itself can curve and evolve. Dark energy may be telling us something profound about what space is when it seems to contain nothing. The emptiest regions of the universe may not be passive at all. They may carry the property that drives cosmic acceleration. It is a strange thought that the nothing between galaxies might be one of the most important things in existence. Of course, we should be careful. Saying empty space has energy is not the same as understanding why it has the value it appears to have, or whether that is the final explanation. We are still at the edge of knowledge here. But even the edge is informative. It tells us that the universe is not built only from objects. It is built from relationships, fields, geometry, and perhaps properties of space itself that our everyday senses never evolved to notice. Your eyes are very good at finding a cup on a table. They are not designed to detect the energy density of the vacuum across billions of light years. For that, humanity needed mathematics, telescopes, detectors, satellites, and many people willing to spend their lives measuring faint things with unreasonable care. The discovery of acceleration is a good example of how science often works against expectation. Scientists expected to measure slowing. They found speeding up. Instead of forcing the data into the old picture, they changed the picture. Not instantly, not carelessly, but through repeated checks, additional observations, and comparison with other evidence. That willingness is one of science's strongest virtues. The universe gets the final vote. Our ideas may be elegant, familiar, and emotionally satisfying, but if the sky disagrees, the sky wins. So where does this leave the original mystery? It leaves us with a universe where gravity pulls everything that can gravitationally interact. But expansion is not simply a motion gravity must cancel. Space itself expands. Gravity slows, shapes, and binds where it can. Dark matter strengthens structure. Dark energy accelerates the larger scale expansion. Galaxies can merge locally while distant galaxies recede faster. The universe can become more structured in some regions while becoming more spread out overall. The answer is not a contradiction, but a hierarchy of scales and ingredients. Perhaps the most comforting part is that the universe we see depends on this complexity. If dark energy had dominated too early, matter might have been pulled apart too quickly for galaxies to form. If gravity had been overwhelmingly stronger on cosmic scales, expansion might have halted or reversed before long-lived stars and planets had time to develop. The fact that we exist means the cosmic balance allowed structure, chemistry, and time. It allowed gravity to build before acceleration became dominant. It allowed stars to live long enough to make heavy elements, planets to cool, and biology to begin its patient experiments. The universe did not have to be this way, but this is the way it is, and we are among its consequences. When you look up at the night sky, most of what you see belongs to the local victory of gravity. Stars are balls of gas held together by gravity. The Milky Way is a galaxy held together by gravity. The constellations are patterns made from stars within our own gravitationally shaped neighbourhood. But beyond what your eyes can see, across distances that require telescopes and long exposure images, the larger expansion continues. The farthest galaxies are not merely distant objects. They are markers of a cosmic history in which space has grown, light has stretched, matter has gathered, and dark energy has begun to set the pace. Dark energy does not make the universe less understandable. It makes it more unfinished. It tells us there is still something fundamental we have not grasped, and there is a certain peacefulness in that. Especially for a sleep science journey, not every question needs to be closed before the night ends. Some questions can remain open like a window onto the dark, letting in a little cool air and a much larger sky. Gravity pulls, space expands, dark energy accelerates that expansion. The galaxies shine for now, held together by gravity, while the distances between the greatest unbound structures continue to grow. And with that, we are close to the widest view of all. We have followed gravity from falling objects to orbiting worlds, from Newton's clockwork cosmos to Einstein's flexible spacetime, from the hot dense beginning to the ongoing expansion, and now into the mystery of dark energy. What remains is not only to ask how the universe can expand, but what that expansion means for everything within it, for galaxies, stars, planets, life, and for us, briefly awake on a turning world, trying to understand the vast quiet motion of the whole. The expanding universe can feel at first like a fact that belongs only to astronomers, tucked away in observatories, written into long papers, and measured by instruments that stare patiently into the dark. It seems far removed from ordinary life. After all, your kettle still boils in the kitchen. Your socks still vanish for reasons science has not fully explained. Your chair does not drift away from you because a distant galaxy is receding. The floor remains under your feet, which is considerate of it. So it is reasonable to ask what this cosmic expansion actually means for everything, not just for galaxies too faint to see, but for the world we live in and the story we tell about where we are. The first answer is reassuring. The expansion of the universe does not mean that everything is being pulled apart. Your body is not expanding. Earth is not expanding. The solar system is not expanding. The Milky Way is not expanding in the same way distant space is expanding. Bound systems remain bound. Atoms are held together by electromagnetic forces. Molecules are held together by chemical bonds. Planets are held together by gravity and the forces inside matter. Moons orbit planets. Planets orbit stars. Stars orbit inside galaxies. These structures are not simply joining the general stretching of space, because local forces are much stronger on these scales. The expansion matters most across the enormous distances between galaxy groups and clusters that are not gravitationally tied together. That is one of the central ideas worth carrying with you. Expansion is not a universal swelling of every object. It is a change in the large-scale distances of the cosmos. The universe can expand while your room stays the same size. Gravity can gather matter into galaxies while the spaces between distant galaxies grow. The moon can remain with Earth while galaxies far beyond our local group recede. There is no contradiction there, only a difference of scale. It is a little like saying a city can grow while a single house remains the same size, or a crowd can spread across a field while two friends standing close together keep holding hands. The whole pattern changes, but local relationships can endure. For us, this means that cosmic expansion is not a danger in daily life. It is not tugging at your blanket, loosening the screws in your furniture, or stretching the distance between your tea and your biscuit, although that last one might explain some evenings rather neatly if it were true. The forces that hold ordinary matter together overwhelm the effect completely. Even Earth and the Sun are not being separated by expansion. The solar system is a gravitationally bound system, and its motions are governed by the Sun's gravity, the planets' interactions, and the long stable dance of orbital mechanics. Expansion belongs to the grand background, not to the small local arrangements that make ordinary existence possible. But on the larger scales, expansion matters enormously. It shapes what we can see, how the universe changes, and what the future will become. When distant galaxies recede from us because space expands, their light is stretched during the journey. The farther the light travels through expanding space, the more stretched it becomes. This stretching is not only a measurement, it is a record of cosmic history. Every distant galaxy we observe is not merely somewhere far away, it is also some time long ago. The universe is a time machine, not in the dramatic sense of stepping into a polished capsule and accidentally meeting your grandfather, but in the simple physical sense that light takes time to travel. Looking outward is looking backward. This makes the night sky a layered history. The moon is seen as it was a little more than a second ago. The sun is seen as it was several minutes ago. Nearby stars are seen years in the past. Distant galaxies are seen millions or billions of years ago. The deepest images we take show galaxies from a time when the universe was much younger. The cosmic background radiation shows us an even earlier stage, when the universe had cooled enough for light to travel freely. Expansion stretches all of this light, and by reading that stretching, astronomers reconstruct how the universe has grown. So one meaning of expansion is that the universe is not static. It is not an unmoving container filled with stars. It has history. It has changed. It was once hotter and denser. It cooled as it expanded. It allowed atoms to form, then stars, then galaxies, then heavy elements, then planets, and eventually, in at least one place we know, life. Expansion is part of the reason complexity became possible. If the universe had remained hot and dense, atoms would not have formed in the familiar way. Stars and planets would not have had the calm conditions they needed. Expansion gave the universe time and room to cool. Gravity then used that cooling universe to build structure. This is one of the most important balances in the whole story. Expansion spreads and cools. Gravity gathers and heats. Expansion increases distances. Gravity creates centers. Expansion makes the universe less dense on average. Gravity takes small density differences and turns them into stars and galaxies. If expansion had been much faster early on, gravity might not have gathered matter efficiently. If gravity had overwhelmed expansion too quickly, the universe might have collapsed before long-lived stars and planets could develop. The universe we see is the result of a long history in which both processes mattered at the right times and scales. This does not mean the universe was designed for us in a scientific sense. It means that our existence depends on a cosmic history with particular conditions. We are not separate from that history. The atoms in your body were made possible by stars, and stars were made possible by gravity acting in an expanding universe. The oxygen you breathe, the calcium in your bones, the iron in your blood, the carbon in every living cell, all of these were forged or scattered through processes tied to stars and their deaths. Expansion made the universe cool enough for stars to form. Gravity made the stars. Stellar lives made the elements. Planetary chemistry made the stage for biology. So when we ask what expansion means for everything, one answer is quietly personal. It helped make everything familiar possible. The expanding universe also changes our sense of location. For most of human history, people imagined Earth as central, or at least as the obvious place from which the heavens were arranged. Then we learned that Earth orbits the Sun. Later we learned that the Sun is one star among many in the Milky Way. Later still, we learned that the Milky Way is one galaxy among vast numbers of galaxies. Expansion goes further. It tells us that there is no special centre of the cosmic expansion. Every distant observer would see other distant galaxies receding. We're not at the centre, but neither are we at an edge. We are inside a universe whose large-scale geometry changes everywhere. That can feel humbling, but not in a bleak way. It means our location is ordinary in the best scientific sense. We do not need to be central to be significant to ourselves. A quiet room on a small planet can still contain a mind capable of asking about the whole cosmos. There is something almost funny about that. The universe expands across scales so large that numbers begin to feel sleepy, and meanwhile a person under a blanket can wonder about it using a brain that occasionally forgets why it walked into the kitchen. We are small, yes, but small things can know large things. That is one of the nicer surprises nature has allowed. Expansion also affects the future of what can be known. Because dark energy appears to be accelerating the expansion, distant unbound galaxies will become harder to observe over time. Their light will be stretched more and more. Many will eventually pass beyond a cosmic horizon, meaning light they emit in the far future will never reach us. They will not disappear from their own neighbourhoods, but they will fade from ours. The universe will become more observationally lonely. The galaxies outside our local gravitationally bound region will slip away from view over immense spans of time. This has a strange consequence. We live in an era when the evidence for the expanding universe is available. Distant galaxies can still be seen. The cosmic background can still be measured. The large-scale structure can still be mapped. Far future astronomers, if they exist after countless ages, may look out and see mostly the merged remnant of our local group, with little direct evidence of the wider universe. They might have a harder time discovering cosmic expansion. The clues we now have could be stretched, dimmed, and hidden beyond reach. In that sense, our time in cosmic history is unusually informative. The universe is old enough to contain galaxies, planets, and observers, but young enough that its wider history is still visible. This is not something to worry about in a personal way. It is not happening on human timescales. Your evening plans are safe from the cosmic horizon. But it is a meaningful thought. Knowledge depends not only on minds, but on the state of the universe those minds inhabit. We can learn about the Big Bang because light from the early universe still reaches us. We can map galaxies because they are still within view. We can infer dark energy because distant supernovae and large-scale patterns remain observable. The expanding universe has given us clues, and for now, we're here while the clues are still readable. The future, if dark energy remains as we currently think, is wide and cold. Stars will not shine forever. New star formation will slow as gas is used up or locked away. Existing stars will age. The brightest stars live quickly and die dramatically. Smaller stars can burn for far longer. Over immense times, galaxies will change, merge, and fade. Our Milky Way and Andromeda are expected to merge in the distant future, forming a larger galaxy. By then, the night sky from any surviving worlds would be very different. The familiar constellations are temporary arrangements, not eternal decorations. Even the stars that seem fixed are moving. There is a gentle sadness in that, but also a kind of clarity. The universe is not a museum. It is not preserving every arrangement forever. Everything changes. Stars form and die. Galaxies merge. Light stretches. Distances grow. Structures evolve. The expansion of the universe places all local stories inside a larger one. The story of Earth, the story of life, the story of human history, all unfold in a cosmos that is itself unfolding. We are not living inside a finished object. We are living inside a process. This process also teaches patience. Gravity works over millions and billions of years. Expansion reveals itself across vast distances. Dark energy becomes important over cosmic eras. Our senses are not built for such scales. We notice falling objects, not receding clusters. We notice sunrise and sunset, not the cooling of the cosmic background. We notice birthdays, not the changing fate of superclusters. To understand expansion, we have to extend our imagination beyond the pace of ordinary life. We have to let telescopes and mathematics become part of our perception. In a way, science gives the human mind new senses, slower and wider than the ones we were born with. There is also a practical meaning to expansion for cosmology itself. It allows us to organize the universe's history into eras. A hot, dense, early phase. A time when light and matter were tightly coupled. A time when atoms formed and light traveled freely. A time when dark matter helped structure grow. A time when stars and galaxies formed. A time when dark energy became dominant. These are not separate stories. They are stages in one connected history. Expansion is the thread that runs through them. It changes temperature, density, distance, and visibility. Without expansion, the timeline of the universe would make no sense as we understand it. And yet, for all this grandeur, the expanding universe does not remove the importance of local life. It may even sharpen it. The fact that distant galaxies are receding does not make a cup of tea less real. The fact that stars are temporary does not make their light less beautiful. The fact that the universe will change beyond recognition does not make the present meaningless. In science, scale is not the same as value. A galaxy is larger than a cell, but a cell is not therefore unimportant. A human life is brief compared with cosmic time, but it is the scale at which love, memory, curiosity, worry, laughter, and rest are actually experienced. The universe supplies the stage, but small beings supply meaning in the way small beings can. This may be one of the most useful emotional lessons of cosmology. We are tiny, but not disconnected. We are temporary, but not irrelevant. We are made of cosmic matter, held together by local forces, living on a planet formed by gravity, warmed by a star, inside a galaxy shaped by dark matter, in a universe whose expansion has carried light across billions of years into our instruments and our eyes. The expanding universe is not somewhere else. It is the full setting of every ordinary moment. When you rest in bed, gravity holds you to Earth. Earth follows the sun. The sun moves within the Milky Way. The Milky Way belongs to a local group. And far beyond that, space expands between the great cosmic structures. The everyday and the cosmic are not separate. They are nested. This returns us to the original question. If gravity pulls everything, why is the universe expanding? Because gravity pulls within a universe whose space can change. Because expansion is not an explosion into emptiness, but the growth of distances within space-time. Because local systems can be bound while the largest unbound distances increase. Because the early universe began in a hot, dense, expanding state. Because gravity slowed and shaped that expansion, building galaxies and clusters. Because dark matter strengthened the growth of structure. Because dark energy now appears to accelerate the expansion on the larger scales. The answer is not one sentence, because the universe is not a one-sentence object. It is a layered history. Gravity has not failed. It is succeeding all around us. It made Earth. It holds the atmosphere. It keeps oceans on the surface. It guides planets and moons. It builds stars. It gathers galaxies. If gravity did not pull, there would be no stable places from which to ask why expansion happens. But gravity does not require every distance in the cosmos to shrink. It acts within the larger behaviour of space-time. Across enormous unbound distances, expansion can dominate. Across even larger spans of time, dark energy can guide the future. The universe is not choosing between gravity and expansion. It is made from their interplay. Perhaps that is why the question is so satisfying. It begins with a simple, everyday feeling. Things fall, gravity pulls, then it opens into the largest possible setting. Space grows, light stretches, galaxies recede, the universe changes. A childlike question becomes a doorway into general relativity, the Big Bang, dark matter, dark energy, cosmic horizons, and the fate of everything. Science often works this way. The best questions are not always the most complicated. Sometimes they are the ones that notice a tension between what we feel and what we observe. Gravity pulls downward here, galaxies move away out there. How can both be true? Following that question carefully teaches us more than either fact alone. And now, after travelling from falling objects to the edge of the observable universe, we can let the answer settle without forcing it to become too small. The universe expands because space-time itself has been expanding since the early hot dense state. Gravity pulls and builds, but it does not stop expansion everywhere. Dark energy appears to make the large-scale expansion accelerate. Local structure remains. Distant space grows. The cosmos is both gathered and widening, both full of islands and full of growing seas between them. So tonight, wherever you are listening from, gravity is holding you gently to a turning planet. Above you, whether the sky is clear or hidden by clouds, the universe continues its quiet expansion. The stars you can see belong mostly to our own galaxy, close enough in cosmic terms to be part of our local gravitational story. Beyond them are galaxies whose light has crossed expanding space for millions and billions of years. Some of that light began its journey before humans existed, before mammals, before life on land, before Earth itself in the case of the most distant sources. It arrives now, faint and stretched, carrying news from a younger universe. There is something peaceful in that thought, not because the universe is small or simple, but because it is understandable in pieces. We do not need to hold all of it at once. We can begin with a falling apple, a moon in orbit, a galaxy's redshift, a faint background glow, a distant supernova, and slowly build a picture large enough to include both gravity and expansion. We can admit what we know, admit what we do not know, and still find comfort in the fact that the cosmos is not random confusion. It has patterns, it has laws, it has history, it has mysteries that can be approached, And if this quiet journey has helped the day loosen its grip a little, if the thought of an expanding universe has made your own worries feel just a bit lighter, I would be glad. You do not need to solve the fate of the cosmos before sleep. The galaxies will continue their slow recession without your supervision. Gravity will keep the Earth beneath you, the stars will keep shining for now, the universe will keep widening in the dark, patiently, silently, on scales far beyond anything we can feel directly. So let your thoughts rest with that balance. Nearby, gravity gathers and holds. Far away, space stretches and carries light across the ages. Somewhere between those two truths, here you are, briefly awake in the long history of the universe, made of old stars, held by a planet, looking outward with a mind that can wonder. Sleep well, fellow traveller, wherever you are in this expanding cosmos,